In this video, we're going to go over fluids. We're going to talk about density, buoyant force, Archimedes principle, Pascal's law, hydraulic lifts, Bernoulli's equation, and things like that. So the first thing that we need to talk about is density. The density of an object is the mass divided by the volume. This symbol is also known as rho. Now don't confuse it with pressure, which I'm going to use capital P. Now if you rearrange the equation, mass is density times volume. The density of water is about 1 gram per cubic centimeter. This is also equal to 1,000 kilograms per cubic meter. The specific gravity of a substance is the density of that substance, let's say substance A, divided by the density of water. So for example, if the density of aluminum is 2.7 grams per cubic centimeter, what is the specific gravity of aluminum? It's the density of aluminum divided by the density of water, and it's simply 2.7. So the specific gravity compares the density of a substance with that of water. Let's try this problem. What is the weight of air inside a spherical balloon of radius 2 meters? And you're given the density of air. Ignore the mass of the balloon. Feel free to pause the video and try this example. So let's say if we have a balloon that has a spherical shape, and there's gas particles inside the balloon. And the gas, even though it's light, it does have mass, so it exerts a downward weight force. What is the weight force of those gas particles? Well, we know that weight is equal to mass times gravity, and mass is density times volume. So the weight of the air inside the balloon is the density times the volume times gravitational acceleration. So it's 1.29 kilograms per cubic meter. That's the density, but we need to find the volume. The volume of a sphere is 4/3 pi r cubed. The radius is 2 meters. So 2 to the third power, that's 8. 8 times 4 is 32. 32 divided by 3 is 10.67 times pi. This is about 33.51 cubic meters. So that's the volume times the gravitational acceleration of 9.8 meters per second squared. So if we multiply these three numbers, this will give us a weight force of 423.6 newtons. Now let's talk more about density. So let's say if you have a beaker containing water, and the density of water is about 1,000 kilograms per cubic meter. Now let's say if you place a chunk of aluminum, what's going to happen? Will it sink or float? The density of aluminum is about 2.7 grams per cubic centimeter, which is 2,700 kilograms per cubic meter. So because aluminum has a higher density than water, it will sink. But let's say if you place an ice cube in water, ice floats on top of water. The reason why ice floats is because the density of ice is less than water. The density of ice is about 917 kilograms per cubic meter. So about 91.7% of the volume of ice will be below the surface of water. So as you can see, heavy objects sink and light objects, they tend to float. Now the same behavior is true for gases. Let's say if you have a balloon that contains helium. Helium is lighter than air, and so helium is going to rise. Now if you have a balloon containing carbon dioxide, it's going to sink. Carbon dioxide is heavier than air. Air molecules are mostly composed of nitrogen and oxygen gas. If you look at the periodic table, oxygen has an atomic mass of 16 times the 2 oxygen atoms that you see here, so the molar mass is about 32 grams per mole. For N2, it's 14 times 2, it's 28. Now, air is about 78 to 79% of nitrogen and approximately 21% oxygen. There's some other gases too, but it's around this number. So we'll say that nitrogen is 78% and then the other 1% is the other gases. So the average molar mass of air is somewhere between 28 and 32. The molar mass of helium is 4. The molar mass of CO2 is 12 plus 16 times 2, that's 44. So because carbon dioxide is heavier than air, it's going to sink. But because helium is lighter than air, it's going to rise. Another fun fact about air is temperature. Hot air rises and cold air sinks. In hot air, the gas particles are further apart, and so hot air is less dense than cold air. In cold air, the gas particles are closer together, and so cold air has a higher density than hot air. So hot air tends to rise, cold air tends to sink. If you live in a 3-story apartment or house, if you turn on the AC, you'll realize that the first floor, or even the basement, will be the coldest area in the house, and the attic is usually the hottest part of the house. That's because all the hot air rises towards the attic and the cold air sinks towards the basement. So this principle is useful for hot air balloons. For example, let's say if you have a very massive hot air balloon, let's say there's a torch. So as you heat up the air inside the balloon expands, and the hot air is less dense or lighter than the surrounding cooler air. So let's say the temperature inside this balloon is maybe 50 degrees Celsius, and outside, let's say it's 20. So as you heat up the air on the inside, the hot air will rise. Now, if you want the hot air balloon to descend, you basically turn this off, and the temperature will decrease, and eventually the weight of the balloon and this package or the people inside it will eventually cause the hot air balloon to descend. So by adjusting the temperature, you can control if it's going to ascend or descend. Now here's a question for you. Is it easier to float in pure water or in salt water? What would you say? So is it easier to float, let's say, in a pool versus the ocean? In a pool, it's mostly pure water. There might be some chlorine inside of it too. But for the most part, the density of the water that you'll find in a typical pool is about 1,000 kilograms per cubic meter. Now, the density of seawater, which is basically salt water, is a little bit higher. It's about 1,025 kilograms per cubic meter. So therefore, it's easier to float in the ocean than in a pool because the density of seawater is higher than that of a typical pool. Now, let's say if you were to go to a very salty lake water, let's say like the Dead Sea or something, the density of the Dead Sea is very, very high. Because it's so salty, if you were to jump in and try to swim to the bottom, you won't be able to. The buoyant force there is so strong that it's going to lift you back to the top and you're going to float right on top of it. The density of the Dead Sea water is about 1240 kilograms per cubic meter. And the higher the density of a fluid, the harder it is to sink. It's easier to float. So it's easier to float in seawater than it is to float in a pool. And by the way, a fluid is anything that could flow. So liquids and gases, because they can both flow, are considered to be fluids. Let's try a problem. An empty bottle has a mass of 25 grams. If you fill it with water, the combined mass is 95 grams. When filled with another fluid, the combined mass is 75 grams. What is the density of this unknown fluid? So what would you do in this problem? So we need to find the volume of the empty bottle of water, because if we have that, then using the mass of the fluid, we can calculate the density of the fluid. Now we know the density of water. It's about 1 gram per cubic centimeter. So what is the mass of the water? The combined mass of the bottle and the water is 95 grams, and the mass of the bottle is 25. So the mass of water must be the difference between these two values. It's 95 minus 25, which is 70 grams. So now let's calculate the volume. Density is equal to mass over volume, and volume is mass over density. So 70 grams of water divided by a density of 1 gram per cubic centimeter tells us that the volume of the bottle is 70 cubic centimeters. Now that we have the volume of the bottle, let's calculate the density of the fluid. So first, we got to find the mass of the fluid. The combined mass of the fluid and the bottle is 75 grams, and the mass of the bottle is 25. So the mass of the fluid is 75 minus 25, so it's 50 grams. Therefore, the density of the fluid is the mass divided by the volume. So it's 50 divided by 70. 50 divided by 70 is about 5 over 7, or 0.714 grams per cubic centimeter. Now that we have the density, if you need to change the units from grams per cubic centimeter to kilograms per cubic meter, multiply by 1,000. So this is equal to 714 kilograms per cubic meter. So that's the answer for this problem. 50 liters of water is mixed with 100 liters of alcohol. What is the density of this mixture? To calculate the density of the mixture, all we need to do is take the total mass, that is the mass of the water, plus the mass of the alcohol, and divide it by the total volume. Because density is the total mass of the solution divided by the volume, or the total volume of the solution. Now, the mass of water is the density of water times the volume of water. And the mass of the alcohol is the density of the alcohol divided by the volume of the alcohol. And we're going to divide it by the total volume. So let's separate this fraction into two smaller fractions. So it's going to be, to keep it simple, P1 V1 divided by V total plus P2 V2 divided by the total volume. Now the reason why I did it that way is so that you could see that it really doesn't matter what the units of volume are because it's going to cancel. If it's in cubic meters or liters, it doesn't matter. It's the ratio that's important. So I don't have to convert liters into cubic meters to get the right answer. So therefore, the density of the mixture is going to be the density of water, which is 1,000, times the volume, which is 50 liters, divided by the total volume, which is 150 liters, plus the density of the alcohol, which is 790, times the volume of the alcohol, which is 100 liters, divided by the total volume of 150 liters. So we can cancel these two zeros. So the first part, 1,000 times 5 divided by 15 is about 333. So that's the contribution from the water. And for the other part, 790 times 10 over 15, it's about 526.6. If we add the two, it's 859.6. So that is the density in kilograms per cubic meter for the mixture. And it makes sense though. Notice that the density of the mixture is between the density of water and the density of aluminum. Now it's not exactly in the middle. If you average 1,000 and 790, if you add the two numbers and then divide by 2, the average between those two numbers is 895. Now, if we were to mix 50 liters of water with 50 liters of alcohol, then the density of the mixture should be 895. But notice that the density of the mixture is closer to the density of the alcohol. It's between 790 and 895 as opposed to 895 and 1,000. Why is the density of the mixture closer to that of alcohol? The reason for that is simple. We mix more of the alcohol than the water. So the density of the mixture should be closer to the density of the pure alcohol than pure water. Now let's talk about pressure. So pressure is the ratio between force and area. The unit for force is newtons, and the unit for area is square meters. The unit for pressure is pascals. 1 Pascal is 1 Newton per square meter. And 1 atm, or 1 atmospheric pressure, is 101.3 kilopascals, kPa, or 101,300 pascals. Now you might see units of torr, or millimeters of mercury. 1 atm is equal to 760 millimeters of mercury, and this is also equal to 760 units of torr. Now these units are usually more associated with chemistry, but in physics, the standard unit for pressure is pascals. Now let's go over the concept of pressure. So let's say if we have a square that is 1 meter by 1 meter, and if we have a larger square that is 10 meters by 10 meters. Now if we apply a force of 100 newtons across the area of this square, and the same force of 100 newtons throughout this entire square, which one has a larger pressure value? Is it the one on the left or the one on the right? So pressure is force over area. The area for the square on the left is 1 times 1. It's 1 square meter. But for the figure on the right, it's 10 meters times 10 meters. So it's 100 square meters. So we have a force of 100 newtons being applied over an area of 1 square meter. So the pressure is force over area. It's 100 pascals. Now, for the figure on the right, 100 newtons is being applied over an area of 100 square meters. So 100 over 100 is 1 Pascal. So the pressure is significantly higher on the figure on the right. So if you apply a force over a very small area, the pressure is going to be very, very high. To illustrate this concept, let's say if you push someone with your hand and you apply a gentle force, it's not going to cause much damage. But let's say if you apply the same force but with a pen and you poke someone with a pen, which one is going to cause more damage? Pushing someone with your hand or applying the same force with a pen? Because the area of a pen is so small, and if you apply the same force over such a small area, the pressure is significantly higher. For example, if you push someone, let's say you apply a force of 100 newtons, and let's say the area of this surface is 1 square meter, the pressure is only 100 pascals. But now let's say if you apply a force of 100, and let's say this area is significantly small, let's say it's 0.01 square meters. 100 divided by 0.01 is 10,000. So the pressure is significantly larger because the area is so much smaller. And that's why poking someone with a pen causes much more damage than pushing someone gently with the palm of your hand. It's because you're applying a significant force over a very, very small area. So the pressure is very large. Now let's say if we have a rectangular box. And let's say the dimensions of the box are 5 meters by 4 meters, and it has a height of 3 meters. And let's say the mass of the box is 100 kilograms. Now, what is the pressure exerted by the box at the ground below? So let's say the box is on this horizontal surface. What is the pressure exerted in this shaded region? So we know that pressure is force divided by area. And the force exerted on the table in the purple shaded region is basically the weight of the box, which is mg. So the mass of the box is 100, the gravitational acceleration is 9.8, and the area of the bottom surface is basically the length times the width. We don't need the height, so it's 5 times 4. So the weight force is 100 times 9.8, which is 9,800 newtons, applied over an area of 20 square meters. So 980 divided by 2 is 490. So the pressure is 490 pascals. Now let's say if we have a very tall container that is filled with water, and let's say the container is sealed, so it's not open to the atmosphere. How can we calculate the pressure at this point in this container? So it's filled with water. How can we find the pressure? Let's say it's a very large tank, and we want to find the pressure 5 meters below the surface. What can we do? So we know that pressure is force divided by area. So the force is going to be the weight of the water, mg, that is currently above this surface where the point of interest is located. So the mass of water exerts a downward force on its cross-sectional area. And that weight force is the mass of the water above it times the gravitational acceleration divided by the area. Now, because we have a fluid, it's best to think of the mass of the fluid as being the density multiplied by the volume. Remember, density is mass over volume. So mass is density times volume. So let's replace M with PV. So the pressure at that surface is the density of the fluid times the volume of the fluid above it multiplied by gravitational acceleration times the area. Now the volume of the water above it is basically the volume of a rectangle. Which is the length times the width times the height. So the volume, as you mentioned before, is L times H times W. Now length times width will give us the area of this surface, which is basically the area of this surface here. So length times width is area, so volume equals area times height. So let's replace V with area times height. So the pressure is going to be the density times the area times the height times gravitational acceleration divided by the area. So we can cancel A. Therefore, the pressure due to the water above this cross-sectional area is equal to the density times the gravity times the height. So now we can calculate it. The density of water is about 1,000 kilograms per cubic meter times G, which is 9.8, times 5 meters. So it's basically 5,000 times 9.8. So the pressure due to the water above that point of interest is 49,000 pascals. Now, what would be the pressure if this container was not closed, if it was open to the environment? In that case, the pressure at this point would be higher because you have the weight of the atmosphere pushing down on the fluid. So in this case, the pressure at the point of interest is going to be called the absolute pressure, that's P, and that's equal to the pressure of the atmosphere plus the gauge pressure. The gauge pressure is simply the pressure that is above the atmosphere. The atmospheric pressure is 101,300 pascals, and the gauge pressure is the pressure due to the weight of the water above that cross-sectional area, so that's the 49,000 pascals. So the absolute pressure at that point is going to be 150,300 pascals. Let's try another problem. Let's say if we have a container that's open to the atmosphere, and we have water, and we also have, let's say, oil. The density of the water, we know it to be 1,000 kilograms per cubic meter, and let's say the density of the oil above it is 700 kilograms per cubic meter. And let's say that the height of the oil is about 4 meters, and the height of the water is about 5 meters. And let's not forget that we have the weight of the atmosphere, basically the weight of all the air molecules above this fluid pressing down on it, exerting its own pressure. So what is the pressure at the bottom of this container? So that pressure, the absolute pressure or the total pressure at that point is the sum of the pressures caused by the weight of the water above that point plus the weight of the oil and the weight of the atmosphere. So the pressure, or the gauge pressure due to water alone, is going to be the density of water times the gravitational acceleration times the height. And the pressure caused by the oil is the density of the oil times G times H plus the atmospheric pressure. The density of water is about 1,000, G is 9.8, and the height of the water is about 5, plus the density of the oil, which is 700 times G, times the height of the oil, which is 4, and then plus the pressure due to the atmosphere, which is 101,300 pascals. So 5,000 times 9.8, that's 49,000. That's the pressure due to H2O alone. And then 700 times 9.8 times 4, that's 27,440 plus the weight of the pressure due to the atmosphere. So if we add the three numbers, 27,440 plus 49,000 plus 101,300, the absolute pressure at this point, or the total pressure, is 177,740 pascals. So basically, you need to add the gauge pressure of the water and the gauge pressure of the oil plus the atmospheric pressure of the air, and that'll give you the total pressure at that point. Now here's a question for you. Let's say if we have a rectangular surface and it's 8 meters by 9 meters, and we want to calculate the total force exerted by the atmosphere on this surface. How would you do it? So we know that pressure is force divided by area. So the force exerted by the atmosphere on this surface is pressure times area. And the area of the surface is the length times the width. So the force exerted by the atmosphere is the pressure of the atmosphere, which is 101,300 pascals, times a length of 9 and a width of 8. So over this large area, the force exerted by the atmosphere is 7,293,600 newtons of force. So that's the entire weight of the air above this particular surface. So all of the molecules, imagine if this was one big vertical column that extended from the ground to outer space. The weight of all of the molecules in this vertical column is equal to this force right here. So that's the weight of the atmosphere above this surface, from the Earth to outer space. Now the next topic of interest is the hydraulic lift. Now this device is filled with a fluid. According to Pascal's principle, the pressure applied to a confined fluid increases the pressure throughout by the same amount. So the pressure that we exert on one side, let's call it the input pressure, is equal to the pressure exerted on the other side, the output pressure. So if we apply a force over this circular area, we're going to exert a pressure. And that input pressure is the input force divided by the area. And an output force will be exerted. And that output force divided by A2 is equal to the output pressure. Let's call it F2. So if we cross multiply, we're going to get the equation F1 A2 is equal to F2 A1. And if we solve for F2 by dividing both sides by A1, we get this equation. F2 equals F1 times the ratio of the areas A2 over A1. So let's make some more space. Now let's apply an input force of 100 newtons. And let's say that the area or the radius of that cylinder is 10 centimeters. And let's say the radius of this cylinder is 30 centimeters. What is the output force that's going to be exerted by this cylinder if we apply an input force of 100 newtons? So using this equation, F2 is equal to F1, which is 100 newtons, times A2, which is basically pi times the radius squared, over A1, which is pi r1 squared. Now we can cancel the pi values. So simply the ratio of the radius of those two circles. So R2 is 30 centimeters, but we need to square it. R1 is 10 centimeters, and we need to square it as well. So the unit centimeters will cancel. We don't really need to change it to meters. So it's 100 times 30 squared, which is 900, divided by 10 squared, which is 100. So F2 is equal to 900 newtons. Now let's think about what this means. The output force was increased by a factor of 9. It went from 100 to 900. So that means that the mechanical advantage of this machine is equal to 9, because it was able to multiply the force, the input force, by a factor of 9. Mechanical advantage is the ratio of the output force divided by the input force. Now, even though the force was multiplied by a factor of 9, it wasn't a freebie, so to speak. There was a cost for it. It wasn't free. So what was the cost that we had to pay to increase the force by a factor of 9? It turns out that the input work that you applied to this device is equal to the output work. So F1 times D1 is equal to F2 times D2. Now let's say if the hydraulic lift went up by 1 meter. That means that we have to apply a force of 100 newtons for a distance of 9 meters, because the work can't be increased. Now we can lose energy by means of friction, but let's say if we have a perfect ideal situation, the input work equals the output work. So the input work is basically a force of 100 newtons times the distance of 9 meters, which is 900 joules. The output work is the same. The machine applies a force of 900 newtons, but it only moves a distance of 1 meter. So it exerts 900 joules of energy. So there's no gain in energy in this system. So we basically apply a small force over a longer distance, and we get a larger force applied over a shorter distance. The concept is similar to that of a lever. A lever allows you to leverage your force to multiply it so you can lift a larger object. For example, let's say if the lever arm on the left side is 8 meters and on the right side it's 2 meters. If you apply an input force of 100 newtons, the output force is going to be 400 newtons. The torque created by F1 is equal to the force times the moment arm, or the lever arm, which is perpendicular to the axis of rotation. It's actually perpendicular to the line of action, and it's between the axis of rotation, or the pivot point. So that's the moment arm. So T1 is 100 times 8. So the torque on the left side is 800 newtons times meters. Now this creates another torque that has the same magnitude. 2 times 400 is also 800. But as you can see with the lever, the smaller force is associated with the longer side, and the larger force is associated with the shorter side. And the same is true for the hydraulic lift. The larger force is associated with the shorter side, and the smaller force is associated with the shorter distance. So now let's work on another problem with the hydraulic lift. So let's say if we want to lift a crate that has a mass of 800 kilograms, and we want to lift it by a distance of, let's say, 50 centimeters. And let's say that the radius of this portion of the hydraulic lift, let's say it's 60 centimeters, and the radius of this circle, let's say it's 10 centimeters. So what is the input force that we need to apply to lift the 800 kilogram crate by a distance of 50 centimeters? And also, what distance do we need to push down on the left side? And also, what is the pressure exerted on this surface? And what is the work that we need to apply to move this object 50 centimeters high? Calculate the work using two formulas. The first thing that we should do is find the output force. The minimum output force that we need to lift the 800 kilogram block or crate is the weight force. So F2 has to at least be equal to the weight force in order to lift this object up 50 centimeters. So F2 is equal to mg, which is 800 times 9.8. So the output force is about 7840 newtons. So now that we have F2, we can calculate F1. F1 divided by A1 is equal to F2 divided by A2. The input pressure is equal to the output pressure, according to Pascal's principle. So looking for F1, A1 is pi r squared, but like in the last example, we can cancel the pi constants. So it's just going to be divided by R1 squared, which is 10 centimeters squared. And we could leave it in units of centimeters. So A2, the pi is canceled, so it's just going to be R2, which is 60 centimeters squared. And F2 is 7840. So let's cross multiply. So F1 times 60 squared. Let's get rid of this. Is equal to 10 squared times 7840. 10 squared is 100 times 7840. That's 784,000 divided by 60 squared. And so F1, or the input force, is 217.8 newtons. Now, how can we calculate the input distance? How far do we need to push this particular cylinder down in order to lift the 800 kilogram block 50 centimeters up? What do we need to do to calculate the answer? The input work must be equal to the output work. And we could find the output work, which is the work required to lift an object against gravity. And whenever you lift an object above ground level, you're increasing the potential energy. So the work required is basically the change in potential energy, which is mg delta h. And the weight force, mg, is basically F2. And the change in height is basically the vertical displacement. So it's going to be force, which is 780 or 7840, times the vertical displacement in meters, which is 0.5 meters. 50 centimeters is half of a meter, and 100 centimeters is 1 meter. So half of 7840 is 3,920 joules. So that's how much energy is required to lift the 800 kilogram crate by 50 centimeters, which means that we need to apply the same amount of energy to push this cylinder down so that this cylinder can go up. So the input work and the output work are both 3,920 joules. So now that we know the value of the input work, we can calculate how far we need to push the cylinder down. It's going to be the input force times the input distance. So work is 3,920. The input force is 217.8. And let's solve for D. So it's 3920 divided by 217.8. So D is about 18 meters, which is pretty high. So we need to apply a force of 218 newtons, and we need to push this cylinder down by a distance of 18 meters in order to lift the 800 kilogram block by only half a meter. So there's no gain in energy. However, the force does increase. So what is the mechanical advantage of this hydraulic lift? The mechanical advantage is the ratio of the output force divided by the input force. So that's 7,840 divided by 217.8. So the mechanical advantage is about 36. So this particular hydraulic lift multiplies the force by a factor of 36. So if you apply a force of 100 newtons, the output force will be 100 times 36, or 3,600 newtons. Now it turns out that there's another way to calculate the mechanical advantage. The mechanical advantage of this hydraulic lift is also equal to the ratio of the input distance divided by the output distance. So we had to push the cylinder on the left by a distance of 18 meters, so that the 800 kilogram crate can go up by 0.5 meters. So 18 divided by 0.5 is 36. So there's a trade-off. If you want to increase the force, you have to apply a smaller force for a longer distance. So the work done is the same in both cases. Now the last thing we need to do is calculate the pressure exerted on the cylinder on the left side. So pressure is force divided by area. The force exerted on the left is 217.8 newtons. And the area is the area of a circle, which is pi r squared. 10 centimeters is 0.1 meters. So 217.8 divided by 0.1 squared. And let's take that result divided by pi. So this is equal to 6,933 newtons. Well, not newtons, but pascals, since this is now the pressure. So that is it for the hydraulic lift. So now the next topic of discussion is the Mercury Barometer. So let's say if we have a beaker, and if we have a tube, and it's filled with mercury. Now this barometer is open to the atmospheric pressure. So the weight of the air exerts a force. And the pressure inside is 0. So the difference in pressure is just the atmospheric pressure. With this information, how can you calculate the height of the mercury column? How high is it above this level? What's the difference in height? Now let's say that you know the density of mercury. The density of liquid mercury is about 13,600 kilograms per cubic meter. And you know the atmospheric pressure. So what is the height of the mercury column? Now to figure this out, we need to understand that the weight of the atmosphere, which is associated with the atmospheric pressure, balances out the weight of this mercury column. And the weight of the mercury column is associated with the gauge pressure. So we could say that because the weight of the atmosphere must balance the weight of that mercury column, the atmospheric pressure must equal the gauge pressure. And the gauge pressure is simply the density of the fluid times the gravitational acceleration times the height. Now we know the atmospheric pressure. It's 101,300 pascals. The density of mercury is 13,600. G is 9.8. So we need to solve for the height. So the height of the mercury column is about 0.76 meters, which is approximately 76 centimeters. Now let's say if we replace mercury with water. How high can the atmosphere support a column of water? How high will the water column be? So we can use the same equation, but this time the density of water is significantly less than that of mercury. So we should expect that we require a higher column to get the same mass of mercury. Mercury is 13.6 times more dense than water. So to get the same mass, we need a height that's 13.6 times greater than the height of Mercury. The density of water is 1,000. G is 9.8. Let's solve for H. So the height of the water column that the atmosphere can support is about 10.3 meters, which is very high. Now remember, the height of the mercury column was 0.76. So if you take 0.76 and multiply it by the ratio of the density of mercury by the density of water, you will get this answer. 0.76 times 13,600 divided by 1,000 is equal to 10.3. So that's another way you can get the same answer if you know the density of one material and you want to find the height of the other material. Let's try this problem. The height of mercury in an open barometer is 64 centimeters, and the height of another fluid is 154 centimeters. What is the density of the fluid, and what is the pressure of the air? So let's draw the open barometer. And it has mercury. So let's calculate the pressure of the air first. So the outside air is going to exert a pressure, and that pressure pushes up the fluid. So the weight of the air equals the weight of this column. So therefore, the pressure of the air is equal to the gauge pressure of that column, which is density times gravity times height. Now for this equation, the density of mercury has to be in the units kilograms per cubic meter. So if it's 13.6 grams per cubic centimeter, that's 13,600 kilograms per cubic meter. G is 9.8, and the height of the mercury column in meters. To convert centimeters to meters, divide by 100. So this is going to be 0.64. So 13,600 times 9.8 times 0.64. That's about 85,299 pascals. So that's the pressure of the air. Now what about the second part of the problem? What is the density of the other fluid? Now, the pressure of the air is equal to the gauge pressure of the other fluid, and that's also equal to the gauge pressure of mercury. So these two are equal to each other. So we could divide by the gravitational acceleration. Those two will cancel. So the density of the fluid times the height of the fluid is equal to the density of mercury times the height of mercury. So the density of the fluid, we're looking for that. The height of the fluid is 154 centimeters. The density of mercury, we can use the units grams per cubic centimeter. If we use those units, then the density of the fluid will also be in grams per cubic centimeter. And the height, we can leave it in centimeters because the height of the fluid is in centimeters. So the unit centimeters will cancel. So the density of the fluid is simply the density of mercury, which is 13.6, times the height of the mercury column divided by the height of the fluid column. So the density of the unknown fluid is 5.65 grams per cubic centimeter. So make sure you understand this. Because mercury has a higher density, the height of the column is going to be less than the height of the fluid that has a lower density. So water has a very low density, but the height of the water column is very, very high. It was about like 10 meters, which is 1,000 centimeters. But mercury, because it's very dense, it has a lot of mass per unit volume. the column for mercury is very low. And so that's why mercury is very useful to use for barometers, temperature gauges, is because there's a lot of mass per unit volume. Now let's say if we have a column, basically an open barometer with a column, and there's going to be two fluids. Here's the first fluid, and here is the second fluid. And let's say on the inside, the pressure is 0. So let's call this fluid A and fluid B. And the height of fluid B, let's say it's 30 centimeters. And the height of fluid A, let's say it's 25 centimeters. And let's say that the density of fluid A is 11 grams per cubic centimeter, and the density of fluid B, let's say it's 14 grams per cubic centimeter. So with this information, what is the atmospheric pressure? How can you calculate it if you have two different fluids? So the atmospheric pressure is the sum of the gauge pressure for fluid B, which represents or is associated with the weight of that column, plus the gauge pressure of fluid A. So it's going to be PA plus PB. So the gauge pressure for fluid A is the density of fluid A times the gravity times the height. And for fluid B is simply PGH as well. So the density for A, now we'll need it in kilograms per cubic meter, so that's going to be 11,000 times G, which is 9.8. And the height of fluid A in meters, 25 divided by 100, is 0.25 meters. And then plus the density of B, which is 14,000 times 9.8, times the height of B, which is 0.3 meters. And we just got to add the two gauge pressures. So 11,000 times 9.8 times 0.25. So the gauge pressure for fluid A is 26,950 pascals. Now for fluid B, it's 14,000 times 9.8 times 0.3. So it's about 41,160 pascals. So now let's add these two values. So the pressure of the atmosphere under these conditions is about 68,110 pascals. So that's how you can calculate it with an open barometer that contains two different fluids. Now let's say if we have an open tube manometer. But we're going to have two of them. So both manometers will contain mercury. But the shapes are going to be a little bit different. So on the outside, it's open to the atmosphere. So this is the atmospheric pressure. And we also have the atmospheric pressure on this side as well. And this is going to be the pressure of the gas, which we can just call it P. And then we have the height of the mercury column, or the height difference, which we'll call h. So how can you write an equation between the pressure of the atmosphere and the pressure inside the gas for each of these situations? So these two pressures, the pressure of the gas and the pressure of the atmosphere, they're going to differ by the gauge pressure, which is pGh. That's the gauge pressure of the mercury column. So how can we find out which equation will be which? So here's a question for you. Which pressure is stronger on the left side? Is it the atmospheric pressure or the pressure of the gas? Notice that the gas pushes down more on the mercury than the atmospheric pressure for the picture on the left. Therefore, this pressure is greater than the atmospheric pressure. And it differs by the gauge pressure of the mercury column. So P is equal to the atmospheric pressure plus the gauge pressure, which is the density times gravity times the height of the mercury column. Now on the other side, the air pushes down more on the mercury column than the gas. So the atmospheric pressure is stronger. So therefore, the atmospheric pressure is equal to the pressure of the gas plus the gauge pressure. So let's work on some examples. Now let's say if we have a fluid, let's say it's some type of oil, and the height difference is about, let's say, 40 centimeters. And the density of this oil, let's say it's pretty heavy. Let's say it's 3 grams per cubic centimeter. And let's say the pressure of the gas is 30 kilopascals. Or rather, let's say the pressure of the atmosphere is simply 101.3 kilopascals. What is the pressure of the gas? So first, we need to find out which pressure is greater, the atmospheric pressure or the pressure of the gas. So the atmospheric pressure pushes down more on the oil than the gas. So the atmospheric pressure is greater than the gas. So the atmospheric pressure is equal to the pressure of the gas plus the gauge pressure of the oil. So that's going to be P plus pGh. So we already have the atmospheric pressure, which we know it to be 101,300 pascals. And this is equal to the pressure of the gas plus the gauge pressure of the oil, which is the density of the oil in kilograms per cubic meter, which is 3,000, times G, and times the height of the column, which is 0.4 meters. So 3,000 times 9.8 times 0.4 is about 11,760. So the pressure of the gas is 101,300 minus 11,760. So it's going to be 89,540 pascals. So that's how you can calculate the pressure of the gas inside a manometer. You simply need to add or subtract the gauge pressure either from or to the atmospheric pressure. And just ask yourself, is the gas pressure, is it less or greater than the atmospheric pressure? and then you can either add or subtract pGh to it. So the pressure that's greater is the one that pushes the fluid further into the manometer. Because the fluid is at a higher level on the right side, that means the pressure of the gas is less than the pressure of the atmosphere. Here it's lower, which means that this pressure is greater. It exerts a greater downward force. Now, how is it that if we place an object that has a higher density than water, it will sink? But if the density is less than water, it will float. Why do light objects float and heavy objects sink? Every object has a downward weight force, so what causes the object to move up towards the surface? Whenever an object is placed in a fluid, there's an upward buoyant force. And according to Archimedes' principle, the buoyant force on a body immersed in a fluid is equal to the weight of the fluid displaced by that object. So what does that mean? Anytime you place an object in a fluid, there's going to be an upward buoyant force. Now, how can we calculate this upward buoyant force? First, we need to draw a better picture. So let's draw a cube. And let's say this cube is submerged in water. Now, at the top surface, there's going to be a gauge pressure. And at the bottom surface, there's another gauge pressure. And these two pressures, because they're at different depths, they're at a different height, the pressures will be different. The pressure at the bottom is higher than the pressure at the top. So because you have a difference in pressure, there's going to be a net upward force. Whenever you have a high pressure and a low pressure, there's a force that is directed from high to low. And so that net force is going to be the buoyant force that's going to lift the object in the upward direction. Now let's say that the top surface has an area called A, and the same is true for the bottom surface. So the force acting on the bottom surface we can call F2, and the force acting on the top surface is F1. So the net force, which is the buoyant force, is the difference between F2 and F1. F2 is the gauge pressure times the area, and F1 is the gauge pressure times the area as well. But these are two different pressures, but the area is the same. So what we can do is factor out the area. So the buoyant force is the area times P2 minus P1, which is basically the change in pressure. Now remember that the gauge pressure is the density times the gravity times the height. So the buoyant force is equal to the area times the density times the gravity times the change in height, which is basically the height of the box. So now area times height is volume. So buoyant force is equal to the density of the fluid times gravity times the volume of the object that is submerged. So this is the buoyant force. That's how you can calculate it. Let's try this problem. So we have a tank that contains water and there's a rectangular block of wood. We want to know if it's going to sink or if it's going to float. So a simple way to find out is to calculate the density of the block and see if it's greater than or less than the density of water. The density of the block is simply the mass divided by the volume. The mass is 175 kilograms. The volume of a rectangle is the length times the width times the height. But we need to convert the dimensions to meters. And we simply need to divide it by 100 to convert centimeters to meters. So 50 divided by 100 is 0.5. So the dimensions are 0.5 meters by 0.75 by 0.8. You have to divide each by 100. So 0.5 times 0.75 times 0.8 gives us the volume of the block, which is 0.3 cubic meters. So now we can take the mass and divide it by the volume. So 175 divided by 0.3 gives us a density of 583.3 kilograms per cubic meter. So notice that the block has a density that's less than that of water. So it's going to float. It's going to rise to the top. So what this means is that the upward buoyant force acting on the block exceeds the weight force that brings the block down. So there's a net upward force that causes it to rise to the surface. So let's calculate the upward buoyant force. Now, according to Archimedes' principle, the buoyant force is equal to the weight of the fluid displaced by the object. And the weight of any object is mass times gravity. So the weight of the fluid is the mass of the fluid times the gravitational acceleration. And we know that mass is density times volume, because density is mass divided by volume. So we can replace the mass of the fluid with the density of the fluid times the volume of the fluid displaced, which is equal to the volume of the object that is submerged. So this is the buoyant force equation that we got earlier in the video. So the density of the fluid is 1,000. The volume of the fluid is, or the volume that's displaced is 0.5 times 0.75 times 0.8, which is the volume of the block, and that's 0.3 cubic meters times the gravitational acceleration of 9.8. So the upward buoyant force is 2,940 newtons. So now, let's calculate the weight force. So the weight force is simply the weight of the object, it's mg. So it's 175 kilograms times g, which is 9.8. So the weight force is basically 1715 newtons. Now the net force is the difference between the upward buoyant force and the downward weight force. So the net force is 2940 minus 1715. So the block experiences an upward force of 1225 newtons. So now that we have the net force, what is the upward acceleration of the block? According to Newton's second law, net force is equal to mass times acceleration. So if the net force is 1225, and if the mass of the block is 175, then the acceleration is 1225 divided by 175. So the block has an upward acceleration of 7 meters per second squared. Now, acceleration is the rate of change of velocity. That means that the upward velocity is increasing by 7 meters per second every second. So after a time of 5 seconds, the upward velocity would be, it's going to be 35 meters per second. And you could use the kinematics equation to find out what the final velocity will be at the top, or you could find displacement using the kinematics equation. So if you need to review that topic, you can find my video on YouTube. So now that we have the net force and the upward buoyant force, what volume of the block will remain above the surface of the water at equilibrium? Now, the buoyant force is proportional to the volume of the object that is submerged. So as the object rises above the surface of water, the buoyant force decreases. And it's going to rise above the water when it reaches equilibrium. That is, when the buoyant force is equal to the weight of the object. At that point, the net force is 0, and the block of wood no longer continues to rise. So when the net force is 0, the upward buoyant force is equal to the downward weight force. So the buoyant force of the object, which is the density of a fluid times the volume submerged times g, is equal to the weight of the object, which is mg. Now the mass of the object is the density of the object times the volume of the entire object times g. So at this point we could divide both sides by g. So we'll get a very useful equation. The density of the fluid times the volume of the fluid displaced, or the volume of the object that is submerged, that is underwater, is equal to the density of the object times the volume of that object. That's the entire volume. So here's our picture. This portion here is the volume that is submerged, the part in green. Whereas the entire block is the volume of the object. So let's see the amount that is above the surface of the water and how much is below it. So the density of the fluid is 1,000. We don't know the volume submerged. We know the density of the object. It's 175 divided by the density, which was actually the density we had it already. It was 0.3. I just forgot for a moment. And the volume of the object is 0.5 times 0.75 times 0.8. Well, actually, the volume is 0.3. I take that back. The density of the object was 175 over 0.3, which is 583.3. So basically, this whole part right here is just the mass of the wood. If you multiply 583.3 times 0.3, you get 175. So this whole thing is just the mass of the object. But I'm going to leave the equation in this form because it's useful if you don't know the mass of the object. Sometimes you'll have the density and the volume of the object. So it's going to be 175 divided by 1,000. So the volume submerged is the mass of the object divided by the density of the fluid, which is 0.175. So if the volume submerged is 0.175 cubic meters, the volume that's above the surface of the water is the total volume, which is 0.3, minus the volume submerged. So 0.3 minus 0.175 is 0.125. So that is the volume of the block that is above the surface of the water. Now we could turn it into a percentage. 0.125 divided by 0.3 is 41.7%. So 41.7% of the block is above the surface of the water. And 0.175 divided by 0.3 gives you the other 58.3%, which is below the surface of the water. That is the amount that's submerged. Now in this problem, we have an ice cube floating on top of liquid mercury. So let's say this is liquid mercury, and here is the ice cube. So we want to find out what fraction of the ice cube will be submerged in liquid mercury. Now we know that the density of the fluid times the volume submerged is equal to the density of the object times the volume of the object. Now let's think about what this equation means, because we know that mass is equal to density times volume. The density of the object times the volume of the object is equal to the total mass of the object. The density of the fluid times the volume of the object submerged is basically the density of the fluid times the volume of the fluid that's displaced. Vs is the same as the volume displaced. So therefore, the density of the fluid times the volume displaced is equal to the mass of the fluid that is displaced. And this is the basic idea behind Archimedes' principle. The mass of the fluid that's displaced is equal to the mass of the object. Now, how can we find the fraction of the ice cube that's going to be submerged? We need to take the volume that is submerged and divide it by the total volume. So we need to rearrange this equation. So first, let's divide both sides by VO. And then let's multiply both sides by 1 over PF. So the fraction that we're looking for is equal to the density of the object divided by the density of the fluid. So it's going to be 917 divided by 13,600. So it's about 0.0674, which represents 6.74%. So about 6.7% of the ice cube will be below the surface of Mercury. The other 93.3% is above the surface of the fluid. So the fraction of the ice cube that's submerged is 0.0674, or 6.7%. So here we have a cube that is made up of wood, and it's 15 centimeters in all three dimensions. Now, we have oil on top, represented in yellow, and water beneath that. And this block of wood it floats literally between the oil and water phases. Now, how is that possible? How can this block of wood just float at that point? It doesn't rise all the way to the top, it doesn't sink all the way to the bottom, it just stays in the middle. Now, we know that heavy objects, they sink, light objects float. So if the density of the oil is 800 and the density of the water is 1,000, that means that the density of this block of wood must be between 800 and 1,000. If it was more than 1,000, it would sink to the bottom. If it was less than 800, it would stay above the oil surface. So because it's between 800 and 1,000, it's somewhere in the middle. Now notice that the cube is 15 centimeters in length. That means that 5 centimeters is below the interface between the oil and the water, and 10 centimeters is above it. So knowing that, would you say that the density of this block of wood, is it between 800 and 900 or 900 and 1000? Now let's say if the block of wood was right in the middle. Let's say if it was 7.5 centimeters above and if it was 7.5 centimeters below the interface. In that case, the density would be exactly 900. It would be the average of 800 and 1000. But notice that the majority of the block of wood is above the interface. So is it between 800 and 900 or 900 and 1000? Well, we know heavy objects sink, light objects float. So because it's higher, it's more into the oil phase, but above and less in the water phase, so to speak. That means it's less dense than 900. It should be between 800 and 900. If more of the block of wood was below the water oil surface, let's say if this was 10 and this was 5, then the density would be between 900 and 1000. So let's go ahead and calculate the density of this block of wood and all the other things that we need to get. Now the first thing we're going to do is calculate the gauge pressure at the lower and upper face of the block. So let's calculate the gauge pressure at this point and at this point. Let's call the pressure at the lower point P2 and the pressure at the upper point P1. So P2 is going to be the gauge pressure of the water and the oil combined. So this is going to be the pressure of H2O plus the gauge pressure of the oil. Now the gauge pressure caused by water is only the portion of the water that is above that point. Anytime you have an object above a certain point, the weight of that object exerts a force on anything below it. And whenever you have a force acting on a certain area, there's a pressure at that point. So the gauge pressure of water is going to be the density of water times G times the height of water above this point, which is 5 centimeters, plus the gauge pressure of oil, which is the density of the oil, times G times the height of the oil above this point. So the height of oil above this point represents the 20 centimeters. It's not 20 plus 5 because the 5 centimeters correlates to the water. But the 20 centimeters is it's all the oil that's above that point. So make sure you don't put 25 because we've incorporated the 5 centimeters from water. So the density of water, which is 1000, times G, which is 9.8, plus the height of the water above P2, that's 5 centimeters, which is 0.05 meters. The density of the oil, that's going to be 800 times G times the height of the oil that's above the point, which is 20 centimeters. Divide that by 100, you get 0.20 meters. 100 times 9.8 times 0.05, that's about 490. And 800 times 9.8 times 0.20 is about 1568. So the total pressure P2, due to the weight of the oil and the water above that point, is 2058 pascals. Now, what about P1? How can we calculate the gauge pressure at this point? Now, notice that there's no water above P1, so the gauge pressure is therefore the pressure of oil above that point, which is equal to pGh. The density of the oil is 800, G is 9.8, but what is the height of the oil? What should we plug in for H? So the height that we need to use is the height of the oil above that point of interest. The total height of the oil layer is 20 centimeters, and the portion of the block that is above the oil-water interface is 10, which means that the height of oil above P1 is also 10, because 10 and 10 is 20. So 10 centimeters is about 0.1 meters if you divide it by 100. Therefore, the gauge pressure at P1 is 800 times 9.8 times 0.1, which is 784 pascals. So now that we have the gauge pressure at P1 and P2, let's calculate the forces that the fluid exert at these points. So if there's a pressure P2, then that must mean that there's a force that the fluid exerts at P2, and there's another force that the fluid exerts at P1. Let's calculate these two forces. We know that pressure is force divided by area. So if you multiply both sides by A, pressure times area is equal to the force. So let's calculate F2 first. So at the lower surface of this cube, it has an area of 15 centimeters by 15 centimeters, or 0.15 meters by 0.15 meters. And the fluid below it exerts an upward force P2, F2. So F2 is going to be the pressure P2 times the area of the lower surface. P2 is 2058 pascals, or newtons per square meter, and let's multiply it by 0.15 meters squared, which is the area of the bottom face of the cube. So F2 is 46.3 newtons. So now we need to calculate F1, which is the force that's exerted on the top face of the cube. So F1 is going to be P1 times A. And P1 is 784 times the area of 0.15 square meters, or 0.15 meters and then square it. So F1 is equal to 17.64 newtons. And F2 is 46.3 newtons. So now that we have the force that the fluid exerts at the bottom and top surfaces, now we can calculate the buoyant force. The buoyant force, which is an upward force, is the difference between F2 and F1. F2 will always be larger than F1 because the pressure at a greater depth is always higher than a pressure at a higher position within the fluid, since there's more weight of the fluid at a lower position. So the buoyant force is F2 minus F1, which is going to be 46.3 minus 17.64. So the upward buoyant force is 28.66 newtons. Now it turns out that there's another way to calculate the buoyant force, and that's using this equation. The buoyant force is also equal to the density of the fluid times the volume of the fluid displaced, which is the same as the volume of the object that is submerged in that fluid, times the gravitational acceleration. So in this problem, there's two fluids. So therefore, the buoyant force is going to be PVG for the water plus PVG for the oil. So you have to be careful in the way you use this equation. So let's start with the water. The density of the water is 1,000. Now what is the volume of the block that is submerged in the water? So now think of a cube. The volume of a cube is basically the length times the width times the height. So if we draw a cube, well, first let me make some space. So here's a rough sketch of a cube. So this is the length of the cube, this is the width. And notice that the cube is not all of it is in the water phase, only a portion. So the height of the cube that's in the water phase is about 5 centimeters. So the length and the width of the cube, that's 0.15 times 0.15, or 0.15 squared, times the height of the cube that's in the water, which is 0.05 times g. So that's the buoyant force due to the water being displaced. That buoyant force is equal to the weight of the object up to this level. Now the rest of the object, the weight of the upper part of the object, is due to the oil. So we need to use the height of the object that's in the oil phase for the second part of the equation. So that's going to be the density of the oil plus the length and the width, which is 0.15 squared, times the height of the cube that's in the oil, which is 10 centimeters as opposed to 5. So this is going to be 0.10 in meters times 9.8. So 1,000 times 0.15 squared times 0.05 times 9.8, that's about 11.025. So that's the buoyant force due to the water alone. And 800 times 0.15 squared times 0.10 times 9.8 is 17.64. So that's the buoyant force due to the oil layer. That's due to the oil being displaced around the upper part of the cube. Now if we add the two values, we're going to get 28.66, which is the total upward buoyant force acting on the cube. So now you know how to calculate the buoyant force provided by the water and the oil, and you know how to calculate the total upward buoyant force. Now, how can we calculate the mass and the density of the block, now that we know the upward buoyant force? So because the block is in equilibrium, it's basically floating between the two layers. That means that the net force, the net upward force on the block is equal to 0, which means that the upward buoyant force has to balance the weight force in order for it to float at the interface. So the buoyant force equals the weight force, which means that the buoyant force of 28.66 is equal to mg, the weight force of the block. So 28.66 divided by the gravitational acceleration will give us the mass of the block, which is 2.924 kilograms. Now that we have the mass, we can calculate the density of the block. Density is mass divided by volume. The mass of the block is 2.924 kilograms, and the density of the cube is basically the side length raised to the third power. It's the length times the width times the height, or 0.15 times 0.15 times 0.15, which is 0.15 meters cubed. And so the density of the block is 866 kilograms per cubic meter, which makes sense. For this block of wood to float between the oil and the water layer, the density has to be between 800, which is the density of the oil, and 1000, which is the density of water. As we mentioned before, if it's more than 1000, it's going to sink to the bottom. If it's less than 800, it's going to float to the top. But if it's between, it's going to float in between the two layers. And since more of the block of wood is in the oil layer, the density has to be between 800 and 900. If the majority of the block of wood was in the water layer, the density would have to be between 900 and 1000. Consider this U-shaped tube. So it's filled with water and then oil is added on top of it. And when it comes to rest, it forms this particular shape. So based on the shape and the relative heights that we see here, how can you calculate the density of the oil? What would you do to find it? Now, it's important to understand that the weight of the oil above the purple line is equal to the weight of the water above the purple line. The masses have to be the same so that it's balanced. Once you understand that, you'll realize that the gauge pressure due to the oil is equal to the gauge pressure due to the water above the purple line. So because the volume of oil above the purple line is greater than the volume of water above the purple line, that means that the oil is lighter. In order to have the same mass, the oil requires a larger volume, which means that the density of the oil is less than the density of water. So we should get an answer that's less than 1000. Let's go ahead and calculate that answer. Since the weight of the fluids above the purple line must be the same, the gauge pressure of the fluids at the purple line must be equal to each other. So the gauge pressure of the oil is equal to the gauge pressure of water at that point, at the purple line. So PGH is equal to PGH. We can cancel G. So now we can calculate the density of the oil. The height of the oil above the purple line is 40 centimeters. The density of water is 1000, and the height of water above the purple line is the difference between 40 and 18, which is 22 centimeters. Now we don't need to convert centimeters to meters because the unit centimeters will cancel. So it's going to be 1000 times 22 divided by 40. So the density of the oil is 550 kilograms per cubic meter, which is less than 1000, since there's more oil above the purple line than water in terms of volume. So if the mass is the same, mass is density times volume. If you increase the volume, the density has to decrease. So since the volume of oil above the purple line is greater than the volume of water, the density of the oil has to be less than the density of the water. If mass is the same, density and volume are inversely related. Now let's say that we have a block of aluminum metal and there's a rope attached to it, and it's suspended in a vacuum. Now, the upward tension force that supports the weight of the aluminum block, let's say it's 1,960 newtons. This is basically the force that a scale would read. So if that's the tension force, how can you calculate the mass of the aluminum block? Now, in order for it to remain suspended in a vacuum, the tension force must be equal to the weight force, such that the net force in the y direction is 0. So if T equals W, that means that the weight force is 1960, which is equal to mg. So 1960 divided by 9.8 will give you the actual mass of the aluminum block as measured in a vacuum. So the mass is 200 kilograms. Now, what about if the block of aluminum was placed in a tank of water? So in this case, what is the tension force in the rope at this point? And what is the apparent mass on the aluminum block if it's fully submerged in water? So there's going to be a downward weight force, but because it's displaced in water, or it's submerged in water, there's an upward buoyant force acting on the block. Now, if it's balanced in this location, the net force in the y direction is equal to 0. Now, the sum of all forces in the y direction is going to be the upward tension force plus the upward buoyant force minus the downward weight force. And it's equal to 0 if it's at rest. So if we solve for the tension force, it's going to be the weight force minus the buoyant force. Now, the tension force, it measures the apparent mass. In the last example, in a vacuum, the tension force measures the actual mass. But if you submerge an object in a fluid, when you lift it up in a fluid, it's going to feel lighter because the buoyant force supports the weight of the object. So as you lift it up, the buoyant force helps you to lift up the object, so it feels lighter when lifting an object in water. But once you lift it out of water, it feels heavier because you no longer have the support of the buoyant force. So the tension force in the rope, it measures the apparent mass, which is mg. The weight force is based on the actual mass, and the buoyant force is the density of the fluid times the volume that's submerged times the gravitational acceleration. So we can divide everything by g. So the apparent mass is equal to the actual mass minus the mass of the fluid displaced, which is the density of the fluid times the volume displaced, or the volume of the object that is submerged. Mass is equal to density times volume. So if we solve for volume, volume is equal to mass divided by density. And if the object is fully submerged, the volume that is displaced by the water is equal to the actual volume of the object when fully submerged, which is the mass of the object divided by the density of the object. So let's replace Vs with m over Po. So the volume that is submerged is equal to the mass of the object divided by the density of that object. So now let's factor out the GCF on the right side of the equation, which is m. So the apparent mass is equal to the actual mass times 1 minus the density of the fluid divided by the density of the object. So this equation is true only when the object is fully submerged. So now let's calculate the apparent mass for this particular problem. So we know that the actual mass of the aluminum block is 200 kilograms. And the density of the fluid, which in this case is water, is 1000. And the density of the object, which is aluminum, is 2700. So if you type this in the calculator exactly the way you see it, you'll see that the apparent mass of aluminum when placed in water is 125.9 kilograms. So the apparent mass is always less than the actual mass. So remember, this is the apparent mass when it's fully submerged in water. Now that we have the apparent mass, we can calculate the tension force. The tension force is the apparent mass times g. So it's just 125.9 times 9.8, which is 1233.8 newtons. So far, we see that the mass measured by an object changes if you place that object in a fluid. So in a vacuum, an object weighs heavier than it would in a fluid. If you place it in water, it weighs lighter due to the upward buoyant force. Now the same is true in air. Air is a fluid, it contains gases. So if you want to measure the true mass of an object in air, you need to take into consideration the density of the air, because air also provides an upward buoyant force for any object displaced within it. So let's try this problem. What is the apparent mass of a 1000 kilogram block of ice in air? So the apparent mass formula is Ma is equal to the true mass of an object times 1 minus the density of the surrounding fluid divided by the density of the object. So the mass of the block is 1000. The density of the air, which is the fluid, is 1.29, and the density of ice is 917. So the apparent mass of this block of ice is about 998.6 kilograms per cubic meter. So because the density of air is very low, the apparent mass is very close to the true mass. It doesn't differ as much. The difference is significant for objects that are light, but objects that are very heavy with a very large density, the difference is negligible. But for light objects, let's say like a piece of paper, then the upward buoyant force provided by air becomes significant. Now let's answer the second part of the question. So let's say if you have a scale and you place a block of ice on top of it, and the scale says that the block of ice is 476.3 kilograms. Now, because it's measured in air, this is the apparent mass. It's not the true mass. So how can you calculate the true mass knowing the density of air and the density of the block of ice? So the apparent mass is 476.3. We need to calculate M, and PF is 1.29, and PO is 917. 1 minus 1.29 divided by 917 is about 0.998593. So 476.3 divided by that number, it gives you a true mass of 476.97 kilograms. So as you can see, the true mass of the object is always going to be higher than the apparent mass. So whatever the scale reads, know that the true mass is slightly higher than the apparent mass. Let's try this word problem. A 15 kilogram block has an apparent mass of 12 kilograms when fully submerged in water. What is the density of the block? So we can use the apparent mass formula to calculate the density of an object submerged in a fluid of known density, and we can also use it to calculate the density of an unknown fluid if we know the density of the object that is in the fluid. So let's rearrange this formula to calculate the density of the fluid and the object. So let's divide both sides by m. So ma divided by m is equal to 1 minus pf over po. Now we're going to take this term, which is negative on the right side, we're going to move it to the left, which is going to be positive on the left side. And we're going to take this term, which is positive on the left, and move it to the right, so it's going to be negative on the right side. So pf divided by po is equal to 1 minus ma divided by mo. Now let's multiply both sides by the density of the object so that these terms cancel. So now we have this equation. The density of the fluid is equal to the density of the object times 1 minus the apparent mass divided by the actual mass. Now let's plug in what we have. So we know that the density of the fluid, which in this case for the first part it's water, we're looking for the density of the block. The apparent mass is 12 kilograms and the actual mass is 15. 1 minus 12 over 15 is about 0.2, and 1,000 divided by 0.2 is 5,000. So the density of the object is 5,000 kilograms per cubic meter. So now that we know the density of the object, let's calculate the density of the fluid. So if we place the same object in an unknown fluid, the apparent mass is found to be 10 kilograms. What is the density of the unknown fluid? So the density of the object is 5,000. The new apparent mass in this unknown fluid is 10 kilograms, and the actual mass is 15. 1 minus 10 over 15 is about 0.33, or 0.33333 repeating, times 5,000 is equal to a density of 1667 kilograms per cubic meter. So that is the density of the unknown fluid. Let's work on this problem. A 60 kilogram block is attached to a rope connected to a vertical spring in a vacuum. If the spring stretches 12 centimeters to support the weight of the block, what is the spring's constant? So a vertical spring can be used as a scale if you want to measure the weight of an object. But first we need to know what the spring constant is. So what you need to do first to measure the spring constant is you need to apply a block which you know the mass of. So here we have a block of known mass, which is 60 kilograms. And so the weight force is going to cause the spring to stretch. Whenever you apply a downward force to stretch the spring wants to go back to its natural length. There's an upward restoring force. It turns out that the tension force that's in the rope is equal to the force required to stretch the spring. So those two are the same. So what is the tension force in this problem? If the net force in the y direction is equal to 0, the upward tension force that supports the weight of the block has to equal the weight of the block. And the tension force is basically the force required to stretch the spring. And according to Hooke's law, F is equal to kx. And the weight force is mg. Now here's a question for you. We know that x represents the amount that the spring is stretched from its equilibrium position. And we have the value of x in centimeters. So if we use 12 centimeters, k is going to be the spring constant in newtons per centimeter. Should we keep x in centimeters or should we convert it to meters? In this problem, it really doesn't matter, but it's best if we keep it in centimeters because when we answer the second part of the problem, it's in centimeters as well. So keep track of the units. So x is 12 centimeters, the mass is 60 kilograms, and g is 9.8. So the weight force is 60 times 9.8, which is 588 newtons, and it stretches the spring by 12 centimeters. So the spring constant is 49 newtons per centimeter. That means that a force of 49 newtons will stretch the spring by 1 centimeter. So therefore, a force of 588 newtons will stretch the spring by 12 centimeters. So now that we have the constant k, we can use that to measure the mass of an unknown object. Now let's answer the second part of the problem. So a cubical block of aluminum of unknown mass is attached to a vertical spring which stretches 54 centimeters in air. So here's the spring, and here's the rope attached to the block. So we have the downward weight force and the upward tension force that supports the weight of the block. And the tension force is the same as the force required to stretch the spring. And let's say this is the original natural length of the spring. X is the amount that the spring is stretched by from its natural length. So how can we calculate the mass of the block? So once again, once the block reaches equilibrium when it no longer stretches the spring, the net force in the y direction is 0, so the tension force equals the weight force. And the tension force is basically the force required to stretch the spring, which is kx, and the weight force is mg. So this time k is 49 newtons per centimeter, and x is now 54 centimeters. So the unit centimeters will cancel, giving us the force in newtons, which is equal to the weight force. Now keep in mind, this is in air. It's no longer in a vacuum. So the mass that we're going to calculate is not the true mass. It represents the apparent mass. The reason why that's the case is due to the fact that air is a fluid. Whenever you have an object placed in a fluid, there is an upward buoyant force. In a vacuum, there is no upward buoyant force, so the tension is equal to the true weight of the object. But in a fluid, the tension equals the apparent weight. So the apparent mass times the gravitational acceleration is really the apparent weight. So what is the apparent weight equal to? Well, for this object to be in equilibrium, the sum of the forces must be equal to 0, meaning the upward tension force plus the upward buoyant force minus the downward weight force is equal to 0. So if you solve for tension, T is equal to the true weight minus the buoyant force. So since T, which is equal to the apparent weight, that apparent weight is the true weight minus the buoyant force. But for this particular problem, we don't have to worry about all of that. What we need to understand is that the tension force is equal to the apparent weight and not the true weight, which means that the tension force is equal to the apparent mass times the gravitational acceleration. Once we understand that, we can find the apparent mass, and then using the other formula, we can calculate the true mass. So let's find the apparent mass. So it's going to be the spring constant, 49, times the amount that the spring is stretched by, which is 54 centimeters. That's equal to the apparent weight, which is 2646 newtons, divided by 9.8. And so the apparent mass is equal to 270 kilograms. So that's how you can calculate the apparent mass of an object using a vertical spring. You need to know the spring constant, and you need to measure with a ruler how much the spring stretches by. And you can calculate the spring constant using a block of known mass and see how much it changes by. And then you can find the mass of an unknown object. So now that we have the apparent mass, let's use this equation. Apparent mass is equal to the true mass times 1 minus Pf divided by Po. So the apparent mass is 270. The mass of the density of the fluid is 1.29 because it's in air. And the density of the object is 2700. So 1 minus 1.29 divided by 2700, it's roughly about 1. It's like 0.9995222. So 270 divided by that number is about 270.13. So in air, the true mass is very close to the apparent mass. They don't really differ by that much. So now that we know the true mass and the apparent mass, how far will the spring stretch if 40% of the aluminum block is submerged in water? So let's draw a new picture. So let's say if we have a tank containing water, and naturally if you place aluminum in water, aluminum's more dense, so it's going to sink to the bottom. But if we attach a rope to it, then it won't sink. The upward tension force will support the weight of the object, and it's still attached to a spring. Now only 40% of the aluminum block is submerged in water. So we're still going to have a downward weight force, but now we have an upward buoyant force provided by the water as well. There's also an upward buoyant force provided by the air as well. So what we're going to do is we're going to calculate the amount that this spring will stretch, neglecting air and also using air. So first, let's neglect the effects of air. Let's just look at the contribution of the buoyant force just by water alone. Now we know that there's an upward tension force which is equal to the force required to stretch the spring. So we got to find out what delta x is, which we could just simply say x. So feel free to pause the video and determine the distance that the spring will stretch if 40% of the aluminum block is submerged in water. So to calculate the amount that the spring will stretch, we need to calculate the tension force, because that tension force is the force that's pulling on the spring, which is equal to kx. We know the value of k. It's 49 newtons per centimeter. So if we can calculate the tension force, then we could find x. So how can we calculate the tension force? So we know that the tension force is equal to the weight force minus the buoyant force. The weight force is mg, and we know the true mass, which is, I'm going to write it on the side, 270.13 kilograms. And then minus the buoyant force, which is the density of the fluid times the volume of the object that is submerged times the gravitational acceleration. So we know the density of the fluid, that's 1,000. So we need to find the volume that is submerged. So what is the volume of the cube? How can we calculate that answer? Now we know that mass is equal to density times volume. So if you want to solve for volume, it's mass divided by density. Now the volume of the object that is submerged is 40% of the aluminum block. So that's 0.4 times the volume of the entire object. And we know that the volume of the entire object is basically the mass of that object divided by the density of the object. So now we can calculate the volume that is submerged. So Vs is equal to 0.4 times the mass of the object, which the true mass is 270.13, divided by the density of the aluminum block, which is 2,700 kilograms per cubic meter. So 270.13 divided by 2,700. So the volume of the aluminum block is about 0.1 kilograms per cubic meter, multiplied by 0.4. So the volume that is submerged, it's about 0.04002. So now that we have the volume submerged, we can now calculate the tension force. So it's going to be mg, which is 270.13 times 9.8 minus the buoyant force due to water, which is the density of water, times the volume submerged, which is 0.04002, times g, which is 9.8. So the weight of the object, 270.13 times 9.8, that's about 2,647.3, minus the upward buoyant force caused by the displacement of water, that's 1,000 times 0.04002 times 9.8. And that's about 392.2. So if we subtract these two numbers, the tension force is equal to 2255.1 newtons. So the tension force is equal to kx, where k is 49 newtons per centimeter. So 2255.1 divided by 49 is equal to 46 centimeters. So that's how far the spring will stretch if the aluminum block is partially submerged. So notice that it stretches 54 centimeters in air, but in water it's only going to stretch 46 centimeters because water supports the weight of the aluminum block by means of the upward buoyant force. So it's going to be less than 54. Now, if we take into account the upward buoyant force of air, the amount that the spring stretches by should be even less. Right now, it's 46.02. So that is the current answer if we don't take into account air. But now let's take into account the effects of air. So this is the buoyant force due to water. Now we must also subtract the buoyant force due to air. Let's call it FB2. So keep in mind, W minus FB is 2255.1. Now we need to subtract it by the buoyant force due to air to get the new tension force. Now the new buoyant force due to air is equal to the density of the air times the volume of the object submerged in air times g. So let's find the volume of the object submerged in air. So if 40% is below water, 60% is above water. So we need to find 60% of the volume of the object. And the volume of the object we know is the mass of the object divided by the density of the object. So it's 0.6 times the mass of the object, which is 270.13, divided by the density of aluminum, which is 2700. So the volume that is submerged is about 0.06003. So now let's calculate the buoyant force due to air. So the density of the air is 1.29, and the volume of the object submerged in air, as we said, it's 0.06003, and G is 9.8. So the buoyant force due to air is very, very small, even negligible. It's about 0.76 newtons. So the tension force is 2255.1. That's without air, but due to the buoyant force of air, it's now going to be 2254.34 newtons. So this tension force is equal to Kx because it's used to stretch the spring. So let's divide it by 49. So due to the effects of air, the spring will stretch by a distance of 46.007 centimeters. So the difference is minute, but there's still a difference. Either case, the spring will stretch by 46 centimeters, whether you take into account air or if you choose not to take into account. A block of iron is attached to a spherical balloon of radius 10 meters that is filled with helium. So let's say this is the balloon, and attached to it we have a block of iron. The radius of the balloon is 10 meters, and it contains helium. We also have the mass of the skin of the balloon. What is the upward buoyant force acting on the balloon? The buoyant force is equal to the density of the fluid. In this case, the surrounding fluid is the air around the balloon, times the volume of the balloon, which is the volume of the object submerged in the fluid, times G. The density of the air is simply 1.29. The volume of a balloon is 4/3 pi r cubed, or pi times 10 to the third power, times G. Ten to the third is 1,000 times 4 pi divided by 3 times 1.29 times 9.8. The upward buoyant force acting on the balloon is 52,955 newtons. Now that we have the upward buoyant force, let's go ahead and calculate the mass of iron that the balloon can support. So the upward buoyant force has to support the weight force of iron. It must also support the weight of the helium that's inside the balloon. And also, it has to support the weight of the balloon itself, because the structure of the balloon has mass. So therefore, the upward buoyant force is equal to the weight of the load, or the iron block, plus the weight of the helium particles inside the balloon, plus the weight of the balloon structure itself. So the buoyant force, which is 52,955, which for now I'm going to write it as P of the fluid times the volume times G. That's equal to the weight of the load, which is the mass of the iron load, times G, plus the weight of helium, which is the mass of helium, times G, plus the weight of the block. So we could divide everything by G. So we have the density of the air times the volume, which equals the mass of the load. Now the mass of helium is equal to the density of the helium gas times the volume of the balloon, plus the mass of the balloon. So what can we do to solve for the missing variable? Now at this point, let's plug in everything that we have. But let's move this and this term to the other side. So the density of the air times the volume of the balloon minus the density of helium times the volume minus the mass of the balloon equals the mass of the iron load. So let's take out V. So now we can solve for M. So the volume of the balloon is 4 over 3 pi times the radius to the third power. The density of the air is 1.29 minus the density of helium, which is 0.179, minus the mass of the balloon, which is 125. So the mass of the load, once you type this information in, it's 4,529 kilograms. Now that we have that information, what is the buoyant force acting on the block of iron? Because the block of iron is also displacing air as well. So the air is going to exert an upward buoyant force. However, the volume of the block of iron is insignificant, so chances are we can neglect it. But let's go ahead and calculate the buoyant force acting on the block of iron. So that buoyant force is going to be the density of the fluid, which is the density of the air, times the volume of the block of iron, which displaces the air, times G. Now we don't have the volume of iron, but we do know the mass and we do know the density. So if mass is density times volume is mass divided by density. So the buoyant force acting on the block of iron is the density of the air times the mass of the block of iron, which is 4529, divided by the density, which is 7,800, times G. So the buoyant force acting on the block of iron, it's about 7.34 newtons. Now keep in mind the buoyant force that was acting on the balloon was 52,955 newtons. So as you can see, the buoyant force provided by the block of iron is insignificant compared to the buoyant force provided by the balloon. And the reason for that is the volume of the balloon is so much more larger than the volume of the block of iron. And so that's why we could ignore this buoyant force. The next thing that we need to talk about is the mass flow rate. The mass flow rate is the amount of mass that passes through a certain point per unit time. So it's the change in mass divided by the change in time. Now we know that mass is density times volume. So the change in mass is the density times the change in volume. Now let's say if we have a pipe which is in the shape of a cylinder. We know that the volume of a cylinder is pi r squared times height. So the volume of the cylinder is the area of the circle, which is pi r squared, times the height, which is basically the length of the pipe. So the change in volume is the area times the change in height. The change in height is basically the displacement. Displacement divided by time is equal to velocity. D over T is equal to V. So therefore we could say that the mass flow rate is equal to the density times the area times the velocity. So if the mass flow rate is equal to density times area times velocity, how can we calculate the volume flow rate? To find the volume flow rate, multiply both sides by 1 over p. Mass divided by density is volume. We know that m is equal to pv. So if you divide by p, mass over density is volume. So delta m over p is delta v. So the volume flow rate is basically the area times the velocity. Now let's work on some problems based on the equations that we just came up with. So water flows through a circular pipe that has a diameter of 20 centimeters. And it flows through the pipe at a speed of 3 meters per second. So what is the mass flow rate? So the mass flow rate is equal to the density of the fluid times the cross-sectional area times the velocity. So the cross-sectional area is basically pi r squared, since it's the area of a circle. So if the diameter is 20 centimeters, the radius is 10 centimeters. But in meters, if you divide it by 100, that's 0.1 meters. So it's going to be the density, which is 1,000, times pi, times r squared, multiplied by the speed of 3 meters per second. So the mass flow rate is about 94.25 kilograms per second. So what this means is that every second, 94.25 kilograms of water passes through this region. Now that we have the mass flow rate, what mass of water will enter a storage tank in 2 hours? So let's say this is the storage tank and water flows out of the pipe into the storage tank. So after 2 hours, how many kilograms of water will enter the storage tank? So we know the mass flow rate is 94.25 kilograms per second. So what we need to do is convert hours into seconds. So we know that there's 60 minutes in an hour, and also there's 60 seconds in a minute. So 2 hours is about 7,200 seconds. So if we take the time in seconds and multiply it by the mass flow rate, the unit seconds will cancel. And we can get the total mass that's going to flow into the tank in 2 hours. So it's 7,200 seconds multiplied by 94.25 kilograms per second. So in 2 hours, 678,600 kilograms of water is going to flow into the tank. Now, what about the last part of the question? How long will it take to add 25,000 kilograms of water to the tank? So we're given mass and we need to find the time. You can use an equation or you can simply use units to get the answer. Let's start with the mass in kilograms. So we have 25,000 kilograms. And we want to convert it to some unit of time. So now we know the mass flow rate, which we set it to be 94.25 kilograms per second. So in 1 second, 94.25 kilograms of water will enter into the tank. So notice that the units kilograms cancel, and now we have the units in time. But let's go ahead and convert it to minutes. So there's 60 seconds in a minute. And let's see if minutes is an appropriate unit. So if we want the answer in seconds, 25,000 divided by 94.25 is about 265 seconds. So let's convert that to minutes. So let's divide that result by 60. So it's going to take about 4.42 minutes for 25,000 kilograms of water to enter into the tank at this rate. Let's try another problem. So water flows through a circular pipe of radius 8 centimeters. So that's this distance here. And it flows through this pipe at a speed of 2.5 meters per second. What is the volume flow rate? The volume flow rate, change in V divided by change in T, is equal to the cross-sectional area of the pipe times the velocity. So the cross-sectional area is the area of a circle, which is pi times the radius squared. 8 centimeters is basically 0.08 meters squared times the speed, which is 2.5 meters per second. So the volume flow rate is about 0.0503 cubic meters per second. So as you can see, here we have square meters times meters to the first power. 2 plus 1 is 3. Now that we have the volume flow rate, how long will it take to fill a pool if the dimensions are 10 by 4 by 15? So first, we need to calculate the volume of the pool, which is length times width times height. 10 times 4 times 15 is about 600 cubic meters. So now that we have the volume and the volume flow rate, we can calculate the time. So let's start with the volume, which is 600 cubic meters. And we know that in 1 second, a volume of 0.05 0.03 cubic meters of water is going to flow through the pipe into the pool. So notice that the volume cancels the cubic meters. So right now this is going to give us the time in seconds, but it's going to be a pretty large number, so let's convert it to minutes. Now we know that there's 60 seconds in a minute, and also there's 60 minutes in a single hour. So these units will cancel and those units will cancel. 600 divided by 0.0503 is about 11,928 seconds. Divided by 60, that's 198.8 minutes. Divided by another 60, this is going to give us a time of 3.3 hours. So that's how long it's going to take to fill a pool with water if the volume of the pool is 600 cubic meters. Now there's some other stuff that you need to know. Let's say if we have another circular pipe, and let's call this position A and position B. The rate at which water flows into the pipe at A equals the rate at which water leaves the pipe at B. And this is associated with the equation of continuity. So the mass flow rate at position A is equal to the mass flow rate at position B. And the mass flow rate is basically the density times the area times the velocity. So this equation is useful if a fluid can be compressed. If you have a compressible fluid like a gas, the density can change. So let's say if the area is constant, but if the density increases, that means that the velocity has to decrease. And let's say if the density is constant. If density is constant, you can cancel these two terms, and then you get another equation, which is A1 times V1, and that's equal to A2 times V2. The area times the velocity, as we mentioned, is the volume flow rate. So if the density is the same, that means that you have an incompressible fluid if the density is constant. So for incompressible fluids, the volume flow rate is constant. So if you increase the area, the velocity will decrease. And if you decrease the area, the velocity will increase. So let's say if we increase the area. So let's say A1 has an area of 2 centimeters squared, and A2 has an area that's twice the value. Let's say it's 4 square centimeters. So if the velocity that enters this cross-sectional area is 5 meters per second, what is the velocity that leaves this pipe? So what's V2? So if we use the equation A1 V1 is equal to A2 V2, A1 is 2, V1 is 5, A2 is 4, so let's find V2. So it's 2 times 5, which is 10, divided by 4, that's 2.5. So if you increase the area by a factor of 2, from 2 to 4, then the velocity will decrease by a factor of 2. So as you increase the area, the velocity decreases proportionally. Now let's say if we decrease the area. Let's say if the radius is 10 centimeters, and let's say over here the radius is now 5 centimeters. if the velocity that enters the pipe, let's say it's 10 meters per second, what is the velocity that leaves this smaller section? So what's v2 if we have v1? So using the same equation, a1 v1 is equal to a2 v2, but this time we have the radius of the pipe at these 2 points. So for a circle, area is pi r squared. Now we can cancel pi, and we don't have to convert centimeters into meters because we have a ratio, and as long as r1 and r2 are both in centimeters, the units will cancel and it's going to work. So r1 is 10 centimeters, v1 is 10, r2 is 5, and let's solve for v2. So 10 squared times 10 is 1,000, divided by 5 squared, which is 25. 1,000 divided by 25 gives you a velocity or speed of 40 meters per second. So if we reduce the radius by a factor of 2, the velocity increases by a factor of 4, because the velocity is inversely related to the square of the radius. So if you decrease the radius by 2, 2 squared is 4, the speed will increase by a factor of 4. If you decrease the radius by 3, 3 squared is 9, the speed will increase by a factor of 9. So in this case, let's say if r1 was 10 over 3 centimeters, then the speed will be 10 times 9, it's going to be 90 meters per second. Now what about the pressure? What happens to the pressure as the speed increases from 10 to 40? Now according to Bernoulli's principle, wherever the velocity of the fluid is high, the pressure is low, and where the velocity is low, the pressure is high. So on the left side, the speed or the velocity is very low, so the pressure is high. And on the right side, the speed is high, so the pressure must be low. Now it makes sense. Whenever you have a pressure, there is a force, because pressure is force over area. So on the left side, if we have a region of high pressure, there must be a very large force that accelerates the fluid towards the right. And on the right side, we have a low pressure, so the force that is created by that pressure is weak. So notice that this force is greater than this one, so therefore there's a net force that accelerates the fluid towards the right, and so it speeds up from 10 meters per second to 40 meters per second. So the potential energy that's stored in the form of this high pressure is converted to kinetic energy as the pressure reduces. So as the pressure decreases from high to low, it loses potential energy, and the water molecules, they gain kinetic energy, and so they speed up. And as you can see, in order for the mass flow rate to be the same, the water has to flow faster in its confined space, so that the amount of water that enters the pipe equals the amount of water that leaves the pipe. Now, if we wish to calculate how the pressure changes along a pipe, we need to use Bernoulli's equation. And Bernoulli's equation comes from the conservation of energy. So let's say if we have the same situation and the pipe accelerates due to the cross-sectional area decreasing. So there's a velocity v1 and it increases to a velocity v2, and we have a pressure p1 and a pressure p2. So if there's a change in pressure, there's going to be a net force which accelerates the fluid. So the work done by this net force should be equal to the change in kinetic energy. And the change in kinetic energy is equal to the final kinetic energy minus the initial kinetic energy. So work plus the initial kinetic energy is equal to the final kinetic energy. And the work done by a force is that force, which is basically the net force, times the displacement. And the initial kinetic energy is 1/2 mv1 squared, and the final kinetic energy is 1/2 mv2 squared. Now we know that pressure is force divided by area. So if you multiply both sides by A, the pressure times the area is equal to the force. So we can replace F with pressure times area times the displacement plus 1/2 mv1 squared equals 1/2 mv2 squared. So at this point, what we're going to do is divide everything by the volume. Area times displacement equals volume. Let's say if you have a cylinder and it has an area A and a displacement or height of d, then the volume is equal to AD. The volume of a cylinder is the area, which is pi r squared, that's the area of a circle, and the vertical or the horizontal displacement is basically the height of the cylinder. So volume equals AD. So we have pressure. We're going to replace AD with volume, which is divided by volume, plus 1/2 m divided by v. Mass divided by volume is density. So we get this equation. And v will cancel. So the pressure plus 1/2 pv1 squared is equal to 1/2 pv2 squared. And I do have to make a correction, because force equals pressure times area, but the net force is really the difference in two forces. It's the difference between F1 and F2. So the net force, it's really F1 minus F2, which is P1A minus P2A. So if you take out A, the net force is A times P1 minus P2, which is basically A times the change in pressure. So this should be delta P, by the way. So change in pressure plus 1/2 PV1 squared is equal to 1/2 PV2 squared. And delta P, we said it's P1 minus P2. So if we add P2 to both sides of the equation, we're going to get this form of the equation. Now, what if the height changes? Because sometimes the pipe needs to go to a different elevated position. So let's say this is the pressure P1, this is the pressure P2, and we have a fluid moving at a speed V1 and here at a speed V2. So the pressure has to apply a force to lift up the fluid against gravity. And anytime the height of the fluid is changing, the gravitational potential energy is changing. So over here, the pressure has to be high. And here the pressure is low, assuming if the velocity is the same as well. So the energy stored in the high pressure will be converted to gravitational potential energy to lift up the object, or to lift up the fluid to a higher position. So energy is going to be transferred from pressure to gravitational potential energy as the fluid goes up. So the work done by the difference in pressure is equal to the change in mechanical energy. The reason being is, depending on the difference in pressure, the pressure could increase the speed as well, which really depends on the relative difference between A1 and A2, the cross-sectional area of the pipe. So if the area decreases, the speed is going to increase. So the pressure can be used to speed up the fluid, or it can elevate the fluid to a different height. So the kinetic energy of the fluid can change, and also the gravitational potential or energy can change. The mechanical energy is basically the sum of the kinetic and the potential energy. So if work equals change in mechanical energy in this particular situation, then it equals the final mechanical energy minus the initial mechanical energy. So work plus initial mechanical energy is equal to the final mechanical energy. And the initial mechanical energy is basically the initial kinetic energy plus the initial gravitational potential energy. And that's equal to the final kinetic energy plus the final potential energy. So P1 is going to exert a force F1, and P2 will exert a backward force called F2. So the work is basically the net force times the displacement, and the net force is the difference between these two forces. So it's F1 minus F2 times D. And we know that force is basically pressure times area. So it's P1A minus P2A times D. And if we factor out A, it's going to be A times P1 minus P2 times D. So let's replace W with the area times the change in pressure times D. Initial kinetic energy is 1/2 mv1 squared, and initial gravitational potential energy is mgh1. And that's equal to final kinetic energy, which is 1/2 mv2 squared, plus final potential energy, which is mgh2. So now, what we're going to do is replace area times displacement with volume. So AD is basically volume times P1 minus P2 plus everything else, which I guess I could just copy this. Now let's divide everything on both sides of the equation by the volume. So these two cancel. So it's P1 minus P2 plus mass over volume is density. So it's 1/2 density times V1 squared plus density times GH1, which equals 1/2 P2 V2 squared plus PGH2 squared, or just PGH2. And now we're going to take this and add it to the other side. So now we have Bernoulli's equation. P1 plus 1/2 PV1 squared plus PGH1 is equal to 1/2 P2V2 squared, or just PV2 squared, plus PGH2 plus pressure 2. So that's Bernoulli's equation. It helps you to see how pressure changes when the height changes or when the speed of the fluid changes. So let's review how this is going to work. So let's say if, as we mentioned before, if the speed increases. So let's say this is V1 and this is V2. Whenever the speed increases, the pressure is going to decrease. So if it's moving slow at the left and if it's moving fast on the right side, whenever the fluid is moving slow, the pressure is high. And whenever the fluid is moving fast, the pressure is low. So you need a high pressure to accelerate the fluid to increase the speed. Whenever the speed increases, there's an acceleration, which means that there's a net force. And the net force created by a fluid is usually due to pressure differences. So as the pressure changes from high to low, the speed is going to increase if, of course, the cross-sectional area decreases. Because as the area decreases, the velocity will increase and the pressure will decrease. Now, let's say if we have a pipe and the height decreases. So let's say this is P1, P2, but the cross-sectional area is the same. So that means that V1 is going to equal V2 if A1 equals A2. So therefore the velocity is constant. Now, whenever an object travels from a high position to a low position, gravitational potential energy is being released. So the question is, what is absorbing that gravitational potential energy? Because typically, when an object slides down an incline, the gravitational potential energy is converted to kinetic energy, and so the object speeds up. So if the cross-sectional area is the same, according to the volume flow rate equation, if A1 equals A2, V1 equals V2, if the fluid is incompressible. So if the fluid density doesn't change, the velocity has to be the same, which means that the kinetic energy is the same. So where does that gravitational potential energy go if kinetic energy is the same? At this position, the pressure is low, but now the pressure is high. So whenever a fluid falls from a high position to a low position, the pressure increases. The gravitational potential energy is being transferred to another form of potential energy, which is stored in the form of high pressure. So whenever you have a fluid at high pressure, that fluid is capable of doing work, because once that pressure changes from high to low, there's going to be a net force. And whenever there's a net force, work can be done, energy can be transferred, because force times displacement is work. So as the fluid travels from a high position to a low position, the gravitational potential energy is being converted in the form of pressure, so the pressure increases. Likewise, if the fluid flows from a high position, or rather from a low position to a high position, the energy that's stored in the form of high pressure is going to be released to push up the fluid to a higher position. So pressure energy is being converted to gravitational potential energy. So let's see if we can put this information to good use. So let's say this is point A, point B, point C, and point D. Let's see how the pressure changes as the fluid moves through this pipe. Now let's review the basic rules. We know that if the cross-sectional area decreases, the fluid is going to speed up, the velocity is going to increase. And whenever the velocity increases, if the speed is high and the pressure is low, so the pressure decreases. And this is at constant height. Now let's say if the area is the same. That means velocity, or the speed, is going to be the same. Now if the height decreases, the pressure will increase. And if the height increases, the pressure will decrease. So now let's go through this problem. As the fluid flows from position A to position B, the cross-sectional area decreases, which means that the velocity of the fluid increases. So that means that the pressure decreases. So if A is at high pressure, B is at a relatively low pressure compared to A. So now let's compare B and C. So the cross-sectional area from B to C is the same. So which means that the velocity is going to be the same. But the height is changing. So the position is decreasing. So gravitational potential energy is being converted to pressure energy, which means that the pressure is going to increase. So C is at a higher pressure relative to position B. Now what about position D? The cross-sectional area increases. So if the cross-sectional area increases, then that means that the velocity has to decrease. And according to Bernoulli's principle, whenever the speed is low, the pressure is high. So the pressure increases. So D is at a higher pressure relative to C. Now let's work on some problems. So let's say if we have a pipe and the cross-sectional area decreases. Let's say the pressure at position A is 150 kilopascals, or 150,000 pascals. What is the pressure at B? If the cross-sectional area at A, let's say it's 30 square centimeters, and A2 is 15 square centimeters. And let's also say that the velocity at position A, let's say it's 4 meters per second. So with this information, if you have V1, P1, A1, and A2, what is P2? How would you calculate the pressure at position B? So feel free to pause the video. So the first thing we need to do is calculate V2 using the volume flow rate equation. A1 V1 is equal to A2 V2. So this equation is true if the fluid is incompressible, where the density is the same. So A1 is 30 square centimeters, V1 is 4, A2 is 15, what's V2? So if the area decreases by a factor of 2 from 30 to 15, the speed should increase by a factor of 2 from 4 to 8. 30 times 4 divided by 15 gives you 8. So that is the velocity at position B. So now that we know the velocity, we can calculate the pressure using Bernoulli's equation. So P1 plus PGH1 plus 1/2 PV1 squared is equal to P2 plus PGH2 plus 1/2 PV2 squared. Now, the height of the center of the fluid is the same, so the gravitational potential energy doesn't change. So energy from pressure is being converted to kinetic energy. So P2 has to be lower than P1 because the speed is increasing. Whenever the velocity is high, the pressure is low. So let's calculate P2. So P1 is 150,000 pascals. Now we're going to use water. So the density of water is 1,000 kilograms per cubic meter. The velocity at position A is 4. We're looking for P2. And V2 is 8. 4 squared is 16 times 0.5, that's 8 times 1,000. So this is 8,000 pascals. And 8 squared is 64, half of that is 32 times 1,000. So over here this is 32,000. So 150,000 plus 8,000 minus 32,000 gives you a pressure value of 126,000. So as the speed increased from 4 meters per second to 8 meters per second, the pressure decreased from 150,000 pascals to 126,000 pascals. So notice that the pressure doesn't change proportionally, so to speak. Even though the speed doubled, the pressure wasn't reduced by half. It decreased, but it wasn't exactly by half. So anytime the speed increases, the pressure decreases. Now let's try another problem. So let's say the cross-sectional area is 10 square centimeters, and at A2 the cross-sectional area is the same. And let's say the fluid is moving at a speed of 5 meters per second. And also, since the cross-sectional area is the same, the speed is the same. Now let's say the pressure at P1, or at position A, let's say it's 150,000 pascals. And the height difference between these two positions, let's say it's 5 meters. What is the pressure P2? So as we mentioned before, anytime the area is the same, the speed will be the same. So the pressure energy is being converted to gravitational potential energy. Anytime the height of the fluid increases, the pressure is going to decrease, assuming the speed remains constant. So, how can we calculate P2? So let's start with Bernoulli's equation. Now, since the velocity is constant, v1 equals v2, so we can eliminate this term. P1 is 150,000 pascals times pgh, the gauge pressure. Now, we're going to say that this is ground level. So position A is at a height of 0, if that's at ground level, so this disappears. P2, we're looking for that. And then pgh, the density of water, times g, which is 9.8, times the height. Position B is 5 meters above the reference level. So 1,000 times 9.8 times 5 is about 49,000. So P2 is 150,000 minus 49,000. So P2 is about 101,000. So as we can see, because the height increased, the pressure decreased from 150,000 pascals to 101,000 pascals. Now it turns out that there's two ways to increase the speed of the fluid. One way is for the fluid to decrease in height. If the object decreases in height, it can speed up, meaning the gravitational potential energy can convert to kinetic energy. The other way to speed up the fluid is to decrease the pressure. If you decrease the potential energy stored in the form of pressure, it can be converted to kinetic energy and the fluid could speed up. And as we know, if the height decreases, the pressure can increase sometimes. Now let's say if the gravitational potential energy decreases by 200 joules. So basically the height is decreasing. Now sometimes this decrease in height can increase the pressure and it can increase the speed. For example, if the energy stored in pressure goes up by 120 joules, that means that the kinetic energy, which is quantified by the speed and the mass, must go up by 80 joules. So a decrease in height is capable of increasing the pressure and the kinetic energy. But now let's say if the height decreases and the gravitational potential energy as a result decreases by 200 joules. But sometimes the kinetic energy can increase more than the amount that the gravitational potential energy decreased by. Now, let's say if the potential energy decreases by 200 joules, but the kinetic energy increases by 300 joules. How is that possible? The only way that the kinetic energy can increase by a magnitude greater than the potential energy is that the pressure has to decrease. So if the pressure loses 100 joules of energy, that 100 joules is transferred to kinetic. And the 200 joules lost by the gravitational potential energy is also transferred to kinetic energy. So if the speed increases by a lot, the height and the pressure could both decrease. So you have multiple situations that you can deal with here. But let's illustrate this example. So let's say if we have another pipe and the height decreases, but also the cross-sectional area increases. So let's say the cross-sectional area is 10 square centimeters. And at this position, the cross-sectional area doubles to 20 square centimeters. And let's say the pressure is 200 kilopascals or 200,000 pascals. And the speed let's say it's currently 10 meters per second. So that's V1. So we need to calculate V2, the new speed, and we want to calculate P2. And let's say the height difference between these two positions, let's say it changes by 10 meters. So first, let's find the new speed. If the cross-sectional area doubles, well actually, I don't want it to double. I want it to decrease so the speed can increase. So let's say the new cross-sectional area is 5. So if the cross-sectional area is reduced by a half, that means the speed has to increase. It has to double. So the speed is 20 meters per second. According to the equation, A1V1 equals A2V2. So if the area decreases, the speed increases. So we know the kinetic energy is increasing. Now, let's calculate the new pressure. So P1 plus P1, or just PV squared, 1/2 PV1 squared, plus PGH1 is equal to P2 plus 1/2 PV2 squared plus PGH2. So let's say this is the reference level. So H2 is 0. P1 is 200,000 plus 1/2 the density of the fluid, which we'll use water, times V1 squared, or 10 squared, plus P times G times H1, which is 10 meters above the reference level, equals P2 plus 1/2 P times V2, or 20 squared. 10 squared is 100 times 1,000 times 0.5. So this is 50,000. And 1,000 times 9.8 times 10 is 98,000. And 20 squared times 1,000 times 0.5 is 200,000 plus P2. So these two cancel, which means P2 is basically 50,000 plus 98,000. So P2 is now 148,000. So now let's think about what happens here. Now what do you think happened? So we know that the speed increased, which means that the kinetic energy of the fluid went up. But notice that the gravitational potential energy decreased because the fluid, it decreased in height. And also the pressure decreased from 200,000 to 148,000. Now, just because the height decreases, it doesn't always mean that the pressure will increase. If the speed was constant, then the pressure has to increase if the height decreases. But in this case, the increase in kinetic energy exceeded the decrease in gravitational potential energy. So in order to increase the kinetic energy further, the pressure had to decrease as well. So let's say if the change in height wasn't 10 meters. Let's say if it's 20. So let's say if the decrease in gravitational potential energy was significant. What's going to happen now? So P1, which is 200,000 pascals, plus PGH, that's 1,000, times G, times the new height difference of 20 meters, not centimeters, plus 1/2 PV squared, or 1,000 times 10 meters per second squared. This is equal to P2. PGH2 is 0 because it's going to be at the reference level, plus 1/2 PV2 squared. So we know this is 20,000, which is going to cancel with this number. So P2 is going to be 1,000 times 9.8 times 20, which is 196,000, plus 1,000 times 10 squared times 0.5, which is 50,000. So if we add those two numbers, we could see that P2 is 246,000 pascals. Now, notice that the pressure is higher than what it was before. In the last example, it was lower than what it was before. So in this case, because we increased the change in height, because it's 20 meters and not 10 meters, the decrease in gravitational potential energy was more than enough to increase the kinetic energy. And so that extra decrease in gravitational potential energy was used to increase the pressure. So whenever the height decreases, the pressure will increase if the speed is constant. If the speed is not constant, the pressure can increase or it can decrease, depending on the relative changes in potential and kinetic energy. So if the speed were to increase by, let's say, a small amount, the pressure will increase as well. However, if the height decreases and if the speed is to increase by a large amount, the pressure has to decrease to also contribute to the increase of that speed and therefore the kinetic energy. So if the speed changes, the pressure may or may not increase. The pressure is most likely to increase if the speed increases by a small amount. But if the speed increases by a large amount, the pressure has to decrease. So it helps to think of the energy changes. So let's say if the gravitational potential energy decreases by 500 joules. If the kinetic energy increases by an amount that's less than the gravitational potential energy, let's say 400, then the pressure energy has to go up by 100. So in this case, the decrease in height caused the speed to increase by a small amount. So the pressure is going to increase by a small amount. Now let's say if the potential energy decreases by 500 joules, but this time the kinetic energy increases by a large amount, an amount that's greater than the decrease of the potential energy. So let's say the kinetic energy increases by 700 joules. To support that increase, the pressure has to go down by 200 joules. So in this case, since the height decreased and since the velocity increased by an amount that's greater than the height, the pressure has to decrease. So let's summarize what we've just considered and consider the relative sizes of the arrows. So if the height decreases and if the speed increases by an amount that's less than a decrease of the height, then the pressure has to increase as well. So notice that the height of these two arrows is equal to the height of that arrow. Let's make this a little bit bigger. So now let's say if the height decreases, but the speed increases by an amount that's greater than a decrease in the height. In this case, the pressure has to decrease as well to support the increase of the speed. So that's how you can tell if pressure is going to go up or if it's going to go down when the height decreases. And if the height decreases, but if velocity doesn't change, then the pressure has to go up by an amount that's equal to the decrease in the gravitational potential energy. So now you know how to tell if the pressure is going to go up or if it's going to go down. So anytime the speed is constant, if the height decreases, pressure goes up. If the height decreases and the speed increases by a small amount, the pressure will go up. If the height decreases, but if the speed increases by a large amount, greater than a decrease of the height, then the pressure is going to go down to support the increase in speed. So hopefully that makes sense. Try this problem. So let's say if we have a similar situation. Let's say that the area is 2 centimeters squared, and over here the area is 4 centimeters squared. And let's say the velocity v1 is currently 2 meters per second at a pressure of 300 kilopascals. And let's say the height difference is 5 meters. So if the area let's reduce the area rather than increasing it. Let's say the area is 1 square centimeters. So if the area reduces by a factor of 2, what is the new velocity? So if we decrease the area by 2, we know the velocity is going to double. Calculate P2. So we know it's going to be 300,000 pascals plus 1/2 the density times the velocity squared plus PGH, and that's equal to PGH2, which is 0, plus P2 plus 1/2 times 1,000 times 4 squared. If you solve for P2, you should get 343,000. So notice that the pressure increased. Now let's say if you decrease the area to an even lower amount. Let's say that the area is decreased to, let's say it decreases by a factor of 4, so to 0.5 squared. If it decreases by a factor of 4, actually, let's say it decreases by a factor of 8. Let's say it's 0.25. What's the new velocity if it decreases by that amount? So if it decreases by a factor of 8, the velocity should increase by a factor of 8. 2 times 8 is 16. So notice that the speed increases by a large amount. Calculate the new pressure. So it's going to be P1, which is 300,000 pascals, plus 1/2 PV squared, plus PGH, and PGH2 is 0, plus P2, plus 1/2 PV squared. So 1,000 times 9.8 times 5 is 49,000. 2 squared is 4 times 1,000, which is 4,000 times half, that's 2,000. So 2,000 plus 49,000, that's 51,000 plus 300,000. The entire left side is 351,000. 16 squared times 1,000 times 0.5 is 128,000. So P2 is 351,000 minus 128,000, which is 223,000, or 223 kPa. So as you can see, as the height decreased and when the velocity increased by a small amount, the pressure went up from 300 kilopascals to 343. Now, when the height decreased by the same amount, but when the velocity increased by a large amount, notice that the pressure went down from 300 kPa to 223 kPa. Because the kinetic energy of the system increased by a lot, the decrease in gravitational potential energy was not enough to support the increase in kinetic energy. So the potential energy stored in the form of pressure had to go down. Now let's consider the reverse situation. Let's say that the pipe goes up this time and the cross-sectional area decreases. How will the pressure change? Will the pressure increase or decrease? So since the area is decreasing, that means that the velocity has to increase, which means that the kinetic energy of the system has to go up. The velocity has to increase if the volume flow rate is to remain constant, meaning that the fluid is incompressible. The density has to remain the same. So if the velocity goes up, kinetic energy has to go up. Now the height is increasing, which means that the gravitational potential energy is increasing as well. So what has to happen to pressure in order for the kinetic energy to go up and the potential energy to go up? So pressure has to decrease. The potential energy stored in the form of pressure has to go down in order that the gravitational potential energy can go up and the kinetic energy can go up. So here, the fluid is moving at a high speed. And here, it's moving at a low speed. So therefore, the pressure has to be high, and here the pressure is low. So the pressure decreases. So if the height increases, the pressure has to decrease to support the increase in height. And if the speed increases, the pressure has to decrease even more to support the increase in speed. So in order for these two forms of energy to go up, pressure has to go down. Now let's say if the area increases rather than decreasing as the fluid travels upward. So if the area increases, that means that velocity has to decrease. And if the speed is decreasing, the kinetic energy has to decrease. Now we know that height is increasing, which means that the gravitational potential energy has to be increasing. So the pressure, is it increasing or decreasing? So it depends. So here are two scenarios. Let's say if the change in kinetic energy is greater than the change in potential energy, gravitational potential energy. And in the other situation, the change in kinetic is less than the change in potential. So if the change in kinetic energy is greater than the change in potential energy, will the pressure have to increase or decrease? Now let's use numbers. So if the change in kinetic energy is greater, let's say that the kinetic energy decreases by 300 joules. That means the potential energy has to go up by something that's less than 300. So let's say the potential energy goes up by 200. That means that the pressure has to go up by 100. Negative 300 is opposite to positive 300. If negative 300 joules of energy was lost by means of kinetic energy, then if 200 joules were gained by potential energy, then the other 100 has to show up as an increase in pressure. So if the decrease in kinetic energy exceeds the increase in potential energy, the pressure has to go up. Now, if the change in kinetic energy is less than the change in potential energy, the pressure has to go down. Now, it helps if you put numbers to it. So let's say if the kinetic energy decreased by 400 joules, and if the gravitational potential energy increased or changed more than that, let's say it changed by 700 joules, then to support the increase in potential energy, the pressure has to decrease by 300. So this is negative, negative, and positive. So the change in energy is 0. Here, if you add these three values, energy is conserved. The change in energy is 0. Now, let's say if you have a tank filled with water and there is an opening. And let's say this is the height of the water, and you want to find out the velocity of water that shoots out of this tank. And let's say the height of water above that position, let's say it's 20 meters. How can you calculate the velocity of water that flows out? Using Torricelli's theorem, the equation that you need is velocity is equal to the square root of 2gh. There's many ways in which you can get this equation. One way is to realize that because the height of the water is decreasing, the potential energy is being converted to kinetic energy. The pressure inside here is basically a vacuum, and the pressure outside here is a vacuum too. It's basically the atmospheric pressure. So there's really no change in pressure. The height is decreasing, and that change in gravitational potential energy is converted to kinetic. So PE is equal to KE. So mgh is equal to 1/2 mv squared. So you can cancel m. And then if you multiply both sides by 2, 2gh is equal to v squared. And if you square root it, the velocity is simply the square root of 2gh. So it's going to be the square root of 2 times 9.8 times the difference in height between these 2 points. and this is going to give you a speed of 19.8 meters per second. Now you can use Bernoulli's equation to get the same result. So you want to calculate the velocity. And let's draw the picture again. So right now, the rate at which the velocity or the height of this fluid is decreasing is very slow. So we could say V1 is approximately 0. We're looking for V2. Now, let's say this is the reference level. Let's say that's ground level. The height difference is basically H1. H2 is basically going to be 0 if we choose that to be the reference level. So we can get rid of this portion of the equation. And once the water exits the opening, it's basically exposed to the atmosphere, which has a pressure of 101.3 kPa. And if this surface is open too, the pressure there is equal to the atmospheric pressure, which is 101 kPa. So these are the same, they cancel. So now, what we have left over is the gauge pressure, PGH1, is equal to 1/2 P1, or just P, V1 squared, which is basically the gauge pressure is associated with the gravitational potential energy, mgh, and that's this pressure here is associated with the kinetic energy of the fluid, which is 1/2 mv squared. So we can cancel the density the same way we can cancel the mass. And then GH is equal to 1/2 V squared. So if you multiply both sides by 2, 2GH is equal to V squared. And if you take the square root, the velocity is equal to the square root of 2GH. So using Bernoulli's equation, or simply using the conservation of energy, you're going to get this equation. So if you increase the height of the water tank, the speed at which water flows out of that tank will increase. Let's try this problem. Water at a pressure of 9 atm flows into a building at ground level at 3.2 meters per second through a pipe 8 centimeters in diameter. The pipe rises 15 meters high and decreases to 3.5 centimeters in diameter. What is the velocity and pressure of the water at this point? So let's draw a picture. So it rises, and then the diameter decreases. So the height difference is 15 meters. Feel free to pause the video and work on this example. Now, if the height increases, and if velocity was constant, the pressure should decrease. The increase in gravitational potential energy is provided by the decrease in the potential energy due to the decrease in pressure. Now, because the area decreases, the velocity has to increase. If the velocity increases, and if the height was the same, the pressure would have to decrease. So in this case, because the gravitational potential energy is increasing and plus the kinetic energy is increasing, the pressure has no choice but to decrease. If the height goes up and the speed goes up, the pressure has to go down. There's no other way. So let's calculate the new pressure. So at ground level, the pressure is 9 atm. That's P1. We need to find P2. But before we can find P2, we got to find V2. So the velocity V1 is 3.2 meters per second. So what is V2? So let's use the volume flow rate equation. A1 V1 is equal to A2 V2. And A is pi r squared. So these two cancel. R1 is basically half of 8 centimeters. If the diameter is 8 centimeters, the radius is 4 centimeters. V1 is 3.2, and R2 is half of 3.5, so it's 1.75. So 4 squared times 3.2 divided by 1.75 squared is equal to a velocity of 16.7 meters per second. So the radius went down from about 4 to less than 2. If the radius decreases by a factor of 2, the speed will have to increase by 2 squared, or a factor of 4. So here the radius decreased by more than 2, so the speed increased by more than 4. So now that we have the speed, let's use Bernoulli's equation to calculate the pressure. So it's going to be P1, which is 9 atm times 101,300. And 1 atm is 101,300 pascals. So 9 times that value gives you P1, which is 911,700 pascals, plus PGH. So let's say this is at ground level. So the height is 0, so there's no PGH value. And then plus 1/2 P1 V1 squared. So the density of water is 1,000 times V1 squared, which is 3.2 squared. Now that's equal to P2 plus PGH, 1,000 times 9.8 times the height of 15, plus 1/2 PV squared. Now 3.2 squared times 1,000 times 0.5, that's 5120 plus 911,700. On the left side, the total pressure value is 916,820. And then 1,000 times 9.8 times 15 plus 0.5 times 1,000 times 16.7 squared. That's 286,445, and then plus P2. So 916,820 minus 286,445 gives you a P2 value of 630,375 pascals. So as you can see, because the height increase and the speed increase, the pressure had to decrease. It decreased from 911,000 pascals to 630,000 pascals. And if you want to convert it back to ATM, divide 630,375 by 101,300. So in ATM, this pressure is about 6.22 ATM. So generally speaking, if you want to raise a fluid to a higher position above ground level, you need to decrease the pressure if the speed is going to be the same. And if you want to increase the speed where the height is the same, you need to decrease the pressure. Now, if water flows to a lower level, and if the speed is the same, the pressure is going to increase. Now, if water is slowing down from high speed to low speed, and if the height is the same, the pressure has to increase. So make sure you understand when the pressure is going to go up and when it's going to go down. But generally speaking, if the speed decreases or if the height decreases, where the other thing is constant, so if the speed decreases and the height is constant, pressure increases. If the speed is constant and the height decreases, pressure increases. Now let's consider this problem. So let's draw a house. Let's say this is the window of the house. Now, if wind blows over the house, what is the net upward force acting on the roof? So let's say this is the side view of the roof. Now there's air underneath the roof and there's air above it. So if there's no wind blowing, the pressure above and the pressure below is the same. So the pressure below exerts a force and the pressure above exerts a force. So if the pressure is the same, these two forces cancel out and the net force is zero. So remember, the pressure of air at sea level is about 101.3 kPa. Now remember Bernoulli's principle. Whenever the velocity is low, the pressure is high. And when the velocity is high, the pressure is low. So if wind passes over the top surface of the roof, you have high speeds, so the pressure is going to be low. So if you have a low pressure system or a low pressure region created by this wind, basically the wind creates a vacuum. It decreases the pressure above the roof. And inside the house, there's not much wind, so the pressure inside is high. Therefore, the upward force exerted by the high pressure is greater by the downward force exerted by the lower pressure. So there's a net upward force that's going to lift up the roof. So if the speed of the wind is very, very high, the pressure inside the house can literally lift up the house. And that's how a hurricane can pull off roofs from homes. The speed of the wind above the roof, if it's fast enough, can decrease the pressure above the roof of the house, causing the pressure inside the house to lift up the house. So if that roof is not attached strongly to the house, it's flying off in a hurricane. Now, how can we quantify the net force? So we need to use Bernoulli's equation. So P2 plus PGH2 plus 1/2 PV1 squared is equal to P1 plus PGH1 plus 1/2 PV2 squared. So we're dealing with air, which means the density is pretty low. And the height difference of the roof is negligible, so we can cancel these two terms. So basically, what we can do is move P1 to the left side. So it's going to be P2 minus P1 on the left side. And let's take this term, move it to the right side. And that's equal to 1/2 PV2 squared minus 1/2 PV1 squared. So the change in pressure is basically 1/2 times P, and then that's V2 squared minus V1 squared. So the change in pressure is equal to this equation. And the change in pressure, which is P2 minus P1, if we multiply both sides by A, P2A minus P1A is equal to 1/2 P times A, V2 squared minus V1 squared. Now the reason why you want to do that is because pressure is force divided by area. So pressure times area is force. So P2A is basically F2 and P1A is F1, which equals what we have here. So let's make some space first. So therefore, F2 minus F1 is basically the net upward force, which is 1/2 the density of the air times the area of the roof times the difference in the squares of the speeds. So now we can calculate the net force. So it's 1/2 times the density of the air times the area of the roof, which is 300 square meters, times the difference in the squares of the speeds. Now, inside the house, there's probably no wind, so we could say it's 0. So V1 is 0. Outside of the house, above the roof, we have a wind speed of 50, so it's going to be 50 squared. So it's 0.5 times 1.29 times 300 times 50 squared. So the net upward force is 483,750 newtons. So as you can see, the force depends on the density of the air, the area upon which the wind acts upon, and the square of the speeds. So if you double the density of air, the force will double. If you double the area upon which the wind acts upon, the force will double. However, if you double the speed of the wind, the force will quadruple, because the force is proportional to the square of the speed. So as the wind speed increases, the force increases exponentially, so to speak. Now, if you think about it, let's say if you have a ball and it's windy, the wind is going to exert a force on the ball, but it's not going to be that much. Now, imagine if it's windy and if you carry, let's say, a very large cardboard with a huge area. So when the wind blows on the cardboard, it's going to exert a large force. The larger the area, the greater the force exerted by the wind. And if the cardboard is large enough, the wind could probably literally carry you away. Now, here's another question for you. Let's say if you have a block of wood or something, and there's a wind speed traveling this way and this way as well. But the wind speed on the right side, let's say it's 40 meters per second, and the wind speed on the left side is 90 meters per second. What is the direction of the net force on this wooden block or this piece of cardboard? Is the net force directed upward, downward, to the left, or to the right? What would you say? Now, I do want to mention something. In the last example, the wind was moving in a direction perpendicular to the surface of the cardboard. In a situation like this, the wind will exert a force in a direction of motion. But in this example, the wind is traveling parallel to the surface of the block. So according to Bernoulli's principle, whenever the wind speed is low, the pressure is high. And whenever the wind speed is high, the pressure is low. So the wind speed is parallel to it. So it's going to create a high pressure when the speed is low, which means that that high pressure will exert a larger force towards the left, and the low pressure will exert a small force towards the right. So therefore, the net force is going to be in the direction of the side with the higher speed. So in the last example, the net force was an upward force because the wind speed above the roof was larger than the speed underneath the roof. And so that's why there was an upward force. Now, the same concept applies to the wing of an airplane. So as an airplane moves forward, the wind that travels on the upper surface has to travel a longer distance. Based on the design of the wing, the upper surface is longer than the lower surface. So the wind that travels above it has to travel at a high speed, and the wind that flows beneath it has to travel at a low speed. So according to Bernoulli's principle, whenever the velocity of the fluid is low, the pressure is high. And whenever the velocity of the fluid is high, the pressure is low. So since we have a high pressure underneath the wing, this creates an upward lift force. So the faster the plane is moving forward, the greater the upward lift force will be. So let's say if you have an object and there's a speed above the object that is about 80 meters per second, and the speed below it is 30 meters per second. Calculate the upward lift force exerted on this block if the area of the block where the wind passes parallel to it is about, let's say, 400 square meters. So we already have the equation. We know that the net force is basically 1/2 the density of the air times the area times the difference in the squares of the speeds. So it's 1/2 the density of air, which is 1.29, times the area of 400 square meters, times V2 squared, which is 80 squared, minus V1 squared, which is 30 squared. So it's 0.5 times 1.29 times 400, that's 258, and then times 80 squared minus 30 squared, which the total force is 1,419,000 newtons.